So here is something worth holding in your mind as you settle in tonight. Right now, wherever you are, the ground beneath you is carrying a scar. A crack that opened 200 million years ago when the Earth itself split apart in fire, and the world that existed before that moment was erased so completely that almost nothing survived. The continents you live on, the shapes you see on maps, the Atlantic Ocean that separates the Americas from Europe and Africa, all of it traces back to that wound. And the creatures that inherited the Earth after that wound healed, the ones whose bones fill museum halls and whose names every child knows, they did not earn their kingdom through strength or speed or intelligence. They inherited it because almost everything else had died. Dinosaurs ruled the planet for 165 million years. That number is so large it almost loses meaning. So let me put it another way. If you compressed the entire reign of the dinosaurs into a single calendar year, all of recorded human history, every empire, every war, every poem, every city ever built, would fit into the last 3 seconds of December 31st. The dinosaurs did not live in a brief window. They dominated Earth for a stretch of time so vast that species arose, flourished, and went extinct entirely within it, never knowing the dinosaurs that came before them or the ones that would follow. And yet, their story begins not with triumph, but with catastrophe. And it ends the same way. Because here is the thread that runs through everything we are going to walk through tonight. The dinosaurs were born from ash. Twice, the Earth was wiped nearly clean by volcanic fire. And twice, the dinosaurs were among the few creatures that walked out of the smoke. Their entire dynasty, every long-necked giant, every armored tank, every sprinting predator, every feathered flyer, all of it grew from the empty spaces left behind by mass death. And then, 66 million years ago, a rock from space finished what volcanoes had started, and the inheritance passed to someone else. To small, furry, nocturnal creatures that had spent 165 million years hiding in burrows and waiting for their moment. Your ancestors. So tonight, as you lie there and let the day fall away, I want to walk you through that story. Slowly, carefully, the way landscapes unfold when you look out a train window without trying to focus on anything in particular. How did the worst disaster in the history of life create the conditions for the greatest dynasty the land has ever seen? What does it mean that the most magnificent animals ever to walk the earth owed their existence to luck, to being in the right place, with the right body, at the right moment? And what does it tell us about life itself that every catastrophe, no matter how total, eventually becomes a beginning? Those are the questions that will carry us through the night, and by the time we reach the end, I think you will find that the story of the dinosaurs is not just a story about the past. It is a story about the logic that governs all living things, including you, including everything alive right now, including whatever comes next. The same pattern that lifted the dinosaurs from the ashes is the same pattern that built the world you are lying in right now. Catastrophe, survival, inheritance, transformation. Over and over, for 4.5 billion years. Let us begin where every honest telling of this story must begin, not with the dinosaurs, with the death that made them possible. 252 million years ago, the Earth looked nothing like the planet you know. The continents were not scattered across the globe the way you see them on a map. They were fused together into a single, enormous landmass called Pangaea, a word that means all lands. And for once, the name was not an exaggeration. Pangaea stretched almost from pole to pole, surrounded on all sides by one colossal ocean, called Panthalassa. If you could have seen it from space, you would not have recognized your planet. The familiar outlines of Africa, South America, Europe, none of them existed yet. Just one vast continent, baking under a sun that rose and set the same way yours does, but over a world that was about to die. And it was a world worth living in. Forests stretched across wide swaths of Pangaea. Reefs thrived along its coastlines. Insects filled the air. Amphibians croaked in wetlands. And on the land, a group of creatures called synapsids. Not quite reptiles, not quite mammals, but something in between, had become the dominant animals. They came in many forms. Some were the size of oxen, lumbering herbivores that browsed on low vegetation. Others were predators with saber-like teeth. They had ruled the land for tens of millions of years, and nothing in their world suggested that rule was about to end. But deep beneath the surface of what is now Siberia, something was building. Heat from the Earth's mantle was pushing upward against the crust, and when it finally broke through, the result was one of the largest volcanic events in the planet's history. We call it the Siberian Traps, and the word traps does not begin to capture what happened. For roughly 1 million years, lava poured out of fissures in the ground across an area the size of Western Europe. Rivers of molten rock flowed for hundreds of miles. Layer upon layer of basalt hardened into the landscape, building plateaus of stone that still exist today. But the lava itself was not the worst of it. The real killing happened in the air. Those eruptions released staggering quantities of carbon dioxide, methane, and sulfur compounds into the atmosphere. The carbon dioxide trapped heat, warming the planet far beyond what most life could tolerate. The sulfur dioxide combined with water vapor to form sulfate aerosols that blocked sunlight, plunging regions into volcanic winter. And when the ash cleared and the warming resumed, the oceans absorbed so much carbon dioxide that they turned acidic, dissolving the shells of creatures that had thrived for millions of years. The dying did not happen all at once. It came in waves, each one worse than the last. Species that survived the initial warming succumbed to acid rain. Those that withstood the acid rain suffocated as oxygen levels plummeted, and those that survived the suffocation starved as the food webs beneath them collapsed. The oceans, once teeming with reefs and fish and invertebrates, became hot, stagnant, and largely empty. The forests on land burned, withered, or simply stopped growing as the soil itself lost its ability to sustain roots. This was the Permian-Triassic extinction event. Scientists sometimes call it the Great Dying, and that name is earned. Roughly 95% of all marine species vanished. 70% of land vertebrates disappeared. Even insects, which had survived almost everything the planet had thrown at them for hundreds of millions of years, were devastated. The reefs, which had taken millions of years to build, crumbled into sand. The forests that had covered Pangaea were reduced to stumps and ash and memory. Think about that for a moment. 95% of marine species, gone. Imagine walking along a shoreline and seeing nothing. No fish, no shells, no darting shadows beneath the surface. The water warm, too warm, nearly 40 degrees in the shallows. It smells of sulfur and rot. The waves lap against black rock and nothing lives in them. Behind you, the land rises in brown and grey folds toward a horizon shimmering with heat. No green anywhere. The soil itself is washing into rivers that carry nothing but sediment, to an ocean that cannot use it. This was the closest life on Earth has ever come to total annihilation. And it sets the stage for everything that follows. Because the story of the dinosaurs does not begin with a roar. It begins with silence. Now, here is something that makes this extinction different from any other. When scientists examine the rocks from the period just after the Great Dying, they find something unexpected. Not bones, not shells, not the remains of animals clawing their way back to life. They find fungal spores. Enormous quantities of them, far beyond what appears in normal geological samples, a sudden spike that dwarfs everything before or after. The fungi had inherited the earth, and in a terrible way, this makes sense. Fungi are decomposers. In a healthy ecosystem, they are part of a cycle. Plants grow, plants die, fungi break them down, nutrients return to the soil, new plants grow. But the Great Dying broke that cycle. Suddenly, there were no new plants growing. The forests were dead, but the fungi were still alive, still hungry, still doing what fungi do. They consumed the dead wood. They consumed the fallen leaves. They consumed the organic matter in the soil itself. With no new growth to replace what was lost, the fungi ate through the accumulated biomass of the Permian like fire through dry grass. The result was a world without forests and without the conditions to make forests. The soil was depleted. The nutrients were gone. The complex communities of microorganisms that healthy forests depend on had been disrupted beyond recognition. Even if seeds had survived, even if spores had drifted into habitable zones, the ground was not ready to receive them. And here is one of the strangest facts in the entire geological record. For roughly 10 million years after the Great Dying, no coal formed anywhere on Earth. Coal requires vast, swampy forests, where dead trees accumulate faster than they can decompose. Those forests did not exist. The swamps did not exist. The organic productivity that coal requires simply was not there. That absence tells us something profound. The recovery from the Great Dying was not just slow, it was fundamentally different from any recovery before or since. Previous mass extinctions had damaged the forests. This one erased them completely. But life, even at its most broken, has a way of refusing to end. Scattered across Pangaea, in river valleys and coastal margins, in cracks in the dying rock, something was still breathing. Bacteria and fungi clung to whatever organic matter remained. A handful of plant species, tough, drought-adapted, slow-growing, held on along riverbanks where moisture still lingered. A few species of fish survived in deeper waters where conditions were slightly less lethal. Some amphibians found pools that hadn't gone completely toxic. And on the land, walking through the ash and the silence, a few survivors remained. Among them was an animal that deserves a moment of attention, because its story tells you something important about what survival actually looks like in the aftermath of catastrophe. Its name was Lystrosaurus, which means shovel lizard, and it was about the size of a pig. It had a barrel-shaped body, stumpy legs, and a face dominated by two downward-curving tusks. It was not beautiful. It was not impressive. It looked, honestly, like something designed by a committee that had given up halfway through. And in the years immediately following the extinction, Lystrosaurus accounted for up to 95% of all land vertebrates on Earth. Not 95% of one region, 95% of every backbone on land, everywhere on Pangaea. No single genus, before or since, has dominated the terrestrial world so completely. How?
partly because it could dig burrows, which offered stable temperatures and protection from the toxic atmosphere, partly because it was a generalist that could eat whatever scraps of vegetation it found, partly because its barrel chest may have housed unusually large lungs, helping it cope with air that held far less oxygen than what you are breathing right now. But mostly, Lystrosaurus survived because it happened to have the right combination of traits for that particular disaster. Not the best traits, not the most impressive traits, just the right ones at the right moment. And that pattern, survival determined not by superiority, but by a lucky match between an organism's traits and the specific nature of a catastrophe, is the pattern that will repeat throughout everything we are going to talk about tonight. It is the pattern that created the dinosaurs, and it is the pattern that, 66 million years ago, would destroy them. But for now, the Earth is quiet. The volcanoes are subsiding. The atmosphere is beginning to stabilize. The oceans are still toxic, still hot, still largely empty. But they are no longer getting worse. The Triassic Period is beginning. And somewhere in the margins of a devastated world, alongside Lystrosaurus and a scattering of other survivors, a group of small, inconspicuous reptiles called archosaurs is breathing, eating, laying eggs. They do not know it yet, but they are the ancestors of everything that will come next: crocodiles, pterosaurs, and dinosaurs. The silence of the early Triassic is vast, but it will not last forever. Because where there is emptiness, life will always find a way to fill it. And the filling is about to begin. The early Triassic was not a place where life flourished. It was a place where life endured. The planet was still reeling from the Great Dying, and recovery was agonizingly slow in ways that are difficult to appreciate until you sit with the timescales involved.
Consider what 10 million years actually means. The entirety of the last ice age, the whole drama of woolly mammoths and saber-toothed cats, and glaciers grinding across continents, lasted about 2.5 million years. Recorded human civilization is roughly 10,000 years. The time between the Great Dying and the first real forests reappearing on Earth was about 4,000 times longer than all of human history. Imagine the patience of a planet rebuilding itself from nearly nothing. There is no hurry in deep time. There is only persistence. The recovery happened in stages, the way a wound heals, not all at once, but from the edges inward. Pioneer species came first, along the coasts of Pangaea, where moisture from the single, vast ocean could still reach the land. Small plants gained footholds. Ferns were among the earliest to return, their spores scattering on the wind, germinating wherever dampness allowed. Ferns are survivors. They do not need flowers or fruit or complex pollination. They need moisture and light, and a patch of soil that has not completely given up, and they will grow. Within a few 100,000 years of the worst of the extinction, patches of green were appearing along riverbanks and in coastal margins. Ferns unfurling their fronds like small flags of defiance against the brown emptiness around them. Behind the ferns came lycopsids, the diminished descendants of the giant club mosses that had built the coal swamps of the Carboniferous. They were small now, scrubby, nothing like the towering forms of their ancestors, but they stabilized soil and added organic matter. Horsetails grew in wet ground wherever streams still ran. And then, slowly, came the conifers. The conifers would change everything. Their needles were coated with wax to prevent water loss. Their seeds were protected in tough cones that could wait years, even decades, for the right conditions. They could grow in poor soil, tolerate drought, and survive temperature swings that would kill most other plants. In the early Triassic, these were not luxuries. These were the minimum requirements for survival, and the conifers met them. Slowly, over millions of years, they spread from coastal refuges inland, their trunks thickening, their canopies rising, their roots breaking rock into something that could begin, once again, to be called soil. By the Middle Triassic, perhaps 20 million years after the Great Dying, something like forests existed again. Not everywhere. The vast interior of Pangaea remained desert, thousands of miles from the nearest ocean, baked by sun, stripped of moisture by mountain ranges and sheer distance. But along the coasts, along the river valleys, in the narrow strips where water flowed, the green was returning. Conifers grew tall. Seed ferns spread their fronds in the understory. Cycads, those palm-like plants with stout trunks and stiff crowns of leaves, began to colonize drier areas. The landscape was not yet lush, but it was alive. And where the plants went, the insects followed. Beetles were among the first to diversify, chewing through dead wood, burrowing into stems, eating leaves and each other. Flies appeared. Cockroaches scuttled through the leaf litter, apparently immune to anything the planet could throw at them. And in what is one of my favorite details from this era, a group of insects called Titanoptera, grasshopper-like creatures reaching about 6 inches in length, began to sing. The males had specialized structures on their wings that produced sound when rubbed together. After millions of years of silence, the forests were filling with noise again. The humming of beetles, the buzzing of flies, and the strange, ancient song of Titanoptera echoing through conifer groves that no human ear would ever hear.
The animals took longer to recover than the plants. This makes sense when you think about it. Animals depend on plants, either directly for food or indirectly through food chains, and until the vegetation was robust enough to support them, large animal populations simply could not exist. But as the forests thickened and the food base expanded, the survivors began to diversify. Lystrosaurus, which had dominated the earliest Triassic so completely, began to fade. As the world grew more complex, as new plants and new habitats emerged, specialists began to outcompete the generalists. Other synapsids evolved, therapsids that were becoming increasingly mammal-like, developing fur, developing better jaws, developing the metabolic efficiency that would one day make mammals the remarkable creatures they are. But for now, they remained small, and their time was still far in the future. Because something else was happening.
A different group of animals was rising, and their ascent would reshape the world in ways that the synapsids could not have imagined. These were the archosaurs. The archosaurs had survived the Great Dying as a handful of small, unremarkable species, but in the empty world of the early Triassic, they found opportunity. They diversified rapidly, splitting into 2 great lineages that would dominate the planet for the rest of the Mesozoic era. One lineage led toward the crocodilians, not the crocodiles you know today, but a staggering variety of forms that filled almost every ecological role imaginable. The other lineage led toward the dinosaurs, and eventually, the birds. In the Middle and Late Triassic, it was the crocodile-line archosaurs, the pseudosuchians, that dominated. And their dominance was impressive,
Some walked on two legs, like dinosaurs would later. Others were armored herbivores the size of rhinoceroses, covered in bony plates. Still others were swift predators that hunted in packs across floodplains. An animal called Postosuchus stood 10 feet tall on its hind legs, with jaws full of teeth that could crush bone. If you had visited the late Triassic and been asked to predict which group of animals would rule the future, you would have bet on the Pseudosuchians without hesitation. They were larger, more diverse, and more ecologically dominant than anything else on land. The dinosaurs existed in this world, but they were marginal players. Mostly small to medium-sized animals occupying niches that the Pseudosuchians had not bothered to fill. The earliest dinosaurs we know of appeared roughly 230 million years ago in what is now South America. Small, bipedal creatures, some no larger than a dog, darting around the edges of ecosystems dominated by much larger Pseudosuchians. They were there, but they were not in charge. And here is where the story gets interesting.
Because the Triassic world, for all its recovery and rebuilding, was not stable. Pangaea was still one enormous landmass, and its geography created extremes. Scorching deserts in the interior, monsoon-drenched coasts, and a climate system prone to sudden, violent shifts. Around 234 million years ago, the planet experienced something called the Carnian pluvial episode, a period of intense, sustained rainfall that lasted roughly 2 million years and transformed ecosystems across Pangaea. The Carnian rains disrupted the established order. Forests expanded into areas that had been dry. Ecosystems that had been stable for millions of years were suddenly rearranged. And the Pseudosuchians, which had been perfectly adapted to the world as it was, found their dominance shaken. Not destroyed, they would hold on for another 30 million years, but shaken enough that new players could gain ground. Among those players were the early dinosaurs.
During and after the Carnian rains, dinosaurs began to spread. Fossils from this period show them appearing across the southern continents, South America, Africa, India, following the same basic body plans but diversifying into new forms. Some were still small predators. Others were beginning to experiment with herbivory, and a few were starting to grow larger, testing the possibilities of size in a world where the old hierarchies were no longer quite as rigid. But the dinosaurs were still not dominant. They were still outnumbered, still outmuscled, still secondary to the Pseudosuchians that had built the Triassic world. For 30 million years after their first appearance, the dinosaurs waited in the margins, surviving without flourishing, present but not powerful. The question of exactly when the first true dinosaurs appeared haunts paleontology. The oldest confirmed dinosaurs date to roughly 230 million years ago, found in rocks from what is now Argentina and Brazil. Animals like Eoraptor and Herrerasaurus, small bipedal creatures with grasping hands and serrated teeth, were recognizably dinosaurian, but still modest in size and ecological importance. They were not yet the rulers of anything. They were newcomers, testing the margins of a world that belonged to others. But the boundary between dinosaur and not quite dinosaur may be blurrier than we once thought. A group of animals called silosaurids, close relatives of dinosaurs, have been discovered in rocks that are even older. These creatures had dinosaur-like teeth, dinosaur-like ankle joints, dinosaur-like hip structures, and yet they do not quite fit the definition of true dinosaurs. Or do they? The debate has divided paleontologists for decades. Some argue that silosaurids were the closest relatives that never quite crossed the line into dinosaur territory. Others argue that they were dinosaurs themselves, early members of one of the major dinosaur lineages. A discovery from Brazil in 2024, a silosaurid called Gondwanax, with 3 fused sacral vertebrae, a trait typically associated with true dinosaurs, blurred the boundary further. If silosaurids are dinosaurs, then the dinosaur lineage originated millions of years earlier than previously thought, and the rise of the dynasty was an even longer, slower process than the fossil record has traditionally suggested. What is clear, regardless of where the line is drawn, is that the ancestors of dinosaurs were already diversifying in the Middle Triassic, spreading across the southern continents of Gondwana and beginning to develop the body plans, the bipedal posture, the efficient respiration, the rapid growth that would eventually carry them to dominance. They were preparing, without knowing it, for the opportunity that the next catastrophe would provide. They did not know it. No creature ever does. But their moment was coming. Not because they were better, not because they were stronger, but because the earth was about to crack open again, and in the fire and chaos that followed, almost everything that stood above them would be swept away. The Triassic world had been built on recovery from one catastrophe. It was about to be torn apart by another. 201 million years ago, the forces that would reshape the planet were already gathering beneath the surface. Deep in the Earth's mantle, hot rock was rising, pressing against the underside of Pangaea, building pressure that had to find release. The supercontinent that had held together for over 100 million years was about to fracture. The crack ran roughly along what would eventually become the Atlantic Ocean.
What is now eastern North America began pulling away from what is now northwestern Africa. And in the gap between them, magma found its way to the surface. The result was the Central Atlantic Magmatic Province, CAMP, and it was catastrophic beyond easy comprehension. Over the course of roughly 600,000 years, lava poured from fissures across an area stretching from what would become Brazil to what would become Morocco. The total volume of erupted material was somewhere between roughly 500,000 to 1.5 million cubic miles. If you spread that volume across the continental United States, it would bury the entire country under more than 650 feet of molten rock. The eruptions came in pulses, 4 distinct episodes, each lasting less than a century, separated by thousands of years of relative quiet. These were not explosive eruptions, like the volcanoes you picture in your mind, mountains blowing their tops in clouds of ash.
These were effusive eruptions, where magma simply poured from cracks in the ground, flowing across the landscape in rivers of liquid stone, building up layer after layer of basalt. But once again, the lava was not the primary killer. The killing came from the gases. Current estimates suggest that camp volcanism released approximately 100,000 gigatons of carbon dioxide into the atmosphere. To understand how much that is, consider that all of human industrial activity since the beginning of the Industrial Revolution has released about 2,000 gigatons. Camp released 50 times more than that. And while it did so over a longer time period, the pace was rapid by geological standards. Fast enough that ecosystems could not adapt. Fast enough that species after species found themselves in conditions their bodies could not handle. The carbon dioxide created a greenhouse effect far beyond anything in the modern world. Global temperatures spiked by 20 to 30 degrees Fahrenheit. But the warming was only part of the assault. Sulfur dioxide, released in enormous quantities, formed aerosols in the upper atmosphere that blocked sunlight and created periods of sudden cooling, volcanic winters that could last years or decades, sandwiched between episodes of intense warming. The climate whipped back and forth between extremes, and most life was caught in the middle. The oceans absorbed carbon dioxide and acidified, just as they had during the Great Dying 250 million years earlier. Shells dissolved, reefs collapsed. Ammonites, those spiral-shelled cephalopods that had recovered from the Permian extinction and diversified across the Triassic seas, were devastated again. Mercury, released in gaseous form during the eruptions, spread globally through the atmosphere, settling into sediments and water, poisoning ecosystems on land and in the sea. The extinction that followed killed approximately 76% of all species on Earth. The reefs died again. Marine food webs disintegrated. And on land, the animals that had dominated the Triassic, the pseudosuchians that had ruled so successfully for so long, were devastated. Think about what that means. The pseudosuchians had survived the Great Dying. They had rebuilt themselves through 50 million years of patient evolution. They had become the dominant large animals on every continent, filling roles as predators, herbivores, and everything in between. And then, in what amounted to a geological instant, they were wiped out. The Rauisuchians, the great crocodile-line predators, some of them 10 feet tall with bone-crushing jaws, vanished completely. The Atosaurs, armored herbivores that had grazed along riverbanks for millions of years, left no descendants. The Phytosaurs, crocodile-like ambush predators of Triassic waterways, disappeared entirely. 30 million years of dominance, erased. Not because the pseudosuchians were poorly adapted, not because they had failed in some evolutionary sense. They were successful, diverse, and well-suited to the world they lived in. They were destroyed because the world changed faster than any adaptation could follow, and the traits that had made them successful in the Triassic were not the traits that would save them from camp. And the dinosaurs? The dinosaurs survived. We do not know exactly why. This is one of the genuinely honest things that science has to say about the Triassic-Jurassic extinction. The mechanism that allowed dinosaurs to pass through it, while so many other groups did not, is still debated. Several possibilities have been proposed, and each of them captures something real about the biology of early dinosaurs. One possibility is their respiratory system. Dinosaurs almost certainly had a system of air sacs connected to their lungs, similar to what we see in modern birds. This system allows air to flow through the lungs in one direction, extracting oxygen far more efficiently than the two-way bellows system that mammals use. In an atmosphere choked with volcanic gases and depleted of oxygen, this advantage may have been the difference between breathing and suffocating. Another possibility is growth rate. Fossils suggest that many early dinosaurs grew quickly, reaching reproductive age faster than the pseudosuchians they shared the world with. In a crisis where survival is uncertain and population crashes are frequent, the ability to reproduce before dying, to get your genes into the next generation before catastrophe strikes again, can be the difference between persistence and extinction. A third possibility, and one that deserves to be stated plainly, is luck. Mass extinctions are chaotic events. The organisms that survive them are not always the ones with the best adaptations. Sometimes they are simply the ones that happen to be in the right place at the right moment. In a burrow when the ash fell, in a valley where temperatures stayed tolerable, near a water source that didn't go toxic. When the world is ending, luck matters more than fitness. Whatever the reason, the result is unmistakable in the fossil record. When the eruptions stopped and the skies cleared and the temperature swings moderated and the oceans slowly began to stabilize, the dinosaurs were there. The pseudosuchians were not. The crocodile-line archosaurs, which had dominated the Triassic so thoroughly, were reduced to a remnant. Small, aquatic, marginal creatures that would survive for hundreds of millions of years as crocodilians, but would never again rule the land. The inheritance had passed. The early Jurassic stretched before the dinosaurs like an empty continent. The ecological roles that pseudosuchians had filled for 30 million years were suddenly vacant. the niches were open. The competition was gone. And the dinosaurs, which had spent their entire existence as marginal, secondary players in a world run by others, stepped into those empty spaces the way water fills a vessel. Not through force, but because there was nothing to stop them. They did not know they were inheriting the Earth. They were just surviving, generation by generation, the way every living thing survives. Eating what was available, reproducing when conditions allowed, spreading into habitats that had been emptied by the extinction and were waiting, green and silent, for something to fill them. But the emptiness would not last, and what the dinosaurs built in the Jurassic, in the long golden age that followed, would become one of the most extraordinary chapters in the history of life on this planet. The second fire had cleared the board.
The game was about to begin again, and this time, the dinosaurs would be the ones playing it. The world that emerged from the Triassic-Jurassic extinction was quieter than it had been, emptier. Ecosystems had been stripped down to their most resilient components, and the silence of the early Jurassic carried an echo of the silence that had followed the Great Dying 50 million years earlier. But this time, the recovery would be faster, and the creatures doing the recovering were different. The early Jurassic spans from roughly 201 million years ago to about 175 million years ago. During those 26 million years, the survivors of the extinction filled the vacant niches, experimented with new forms, and laid the foundations for the world that would follow. And among those survivors, the dinosaurs were the ones with the most room to grow. On land, the transformation was striking.
The pseudosuchians that had dominated Triassic ecosystems were gone, and the dinosaurs that survived the extinction found themselves in a world where the competition that had kept them small and marginal for 30 million years had simply vanished. Imagine a forest where all the tall trees have been removed. The plants that lived in the understory, the ones that had always been shaded, suddenly have access to all the sunlight they need. That is roughly what happened to the dinosaurs at the beginning of the Jurassic. The ceiling above them had been lifted, and they responded by growing. The theropods, the bipedal carnivorous dinosaurs, were among the first to capitalize. Dilophosaurus, one of the best-known early Jurassic predators, reached about 20 feet in length, far larger than most Triassic dinosaurs. It had distinctive paired crests on its skull, probably used for display, and jaws filled with teeth suited for grasping and tearing flesh. Dilophosaurus was not yet the apex predator that later theropods would become. It was more lightly built, more agile, but it was successful in its time, hunting in environments still reorganizing after the extinction. Meanwhile, the herbivorous dinosaurs were undergoing a transformation that would eventually reshape the planet. The prosauropods, which had appeared in the late Triassic as relatively modestly sized animals, the largest, Plateosaurus, weighed perhaps as much as a small car, were transitioning into true sauropods. The body plan was already recognizable. Long necks for reaching vegetation, columnar legs for supporting increasing weight, small heads relative to body size. But in the early Jurassic, these animals had not yet reached gigantic proportions. They were perhaps 30 to 50 feet long, large by the standards of their time, but modest compared to what was coming.
The forests that these early Jurassic dinosaurs inhabited were different from modern forests in ways that went beyond the absence of familiar animals. There were no flowering plants. Angiosperms would not evolve for another 70 or 80 million years. Instead, the vegetation was dominated by gymnosperms, conifers forming canopy layers, cycads growing in understory and open areas, ginkgos spreading along waterways, ferns carpeting the forest floor. Horsetails grew in wet ground along streams. The overall effect was green and lush in wetter regions, with a structure recognizable as a forest, but composed of entirely different plants than anything you would see today. If you walked through it, you would understand the concept of trees and understory and forest floor, but you would not recognize a single species. The absence of flowers meant the absence of fruit. The absence of grass meant the absence of meadows.
Instead of colorful blossoms and open fields, the Jurassic landscape was an endless variation on green, dark conifer needles above, lighter fern fronds below, stiff cycad leaves catching the light in between. The pollination that happened was simpler than what flowers would later achieve. Wind carried spores, cones attracted early insects, but there was none of the elaborate co-evolution between flowers and their pollinators that defines so much of the modern world. These forests were recovering from the extinction, just as the animals were, and in some regions, the recovery was slow. Areas devastated by volcanic activity or climate extremes took time to revegetate. But gradually, over millions of years, the plant communities thickened and stabilized, and as they did, they provided the base upon which the entire Jurassic ecosystem would be built. Because without plants, nothing else works. Every herbivore depends on them. Every predator depends on the herbivores.
The plants were not background scenery. They were the engine. In the oceans, recovery was also underway, though it carried its own pace and its own drama. Ammonites, those coiled cephalopods that had been devastated by the extinction, began to diversify again, evolving rapidly from the handful of lineages that survived. Ichthyosaurs, which had barely made it through as a few remnant species, began to diversify as well. Their dolphin-like bodies, streamlined and built for speed, proved extraordinarily successful, and new species evolved with different sizes and different hunting strategies. Some grew large, becoming apex predators of the early Jurassic seas. Others remained smaller and more agile, pursuing fish and squid in coastal waters. Plesiosaurs made their first significant appearance during this time, evolving from ancestors that had survived the extinction as small, relatively unremarkable marine reptiles. The classic body plan: long neck, small head, 4 large flippers, broad body, was emerging. Though the earliest plesiosaurs were more modest than the forms that would appear later. They were testing their unusual anatomy through evolutionary trial and error, discovering that a long neck combined with powerful flippers could be an effective way to hunt in shallow seas, where fish and squid congregated. Pangaea was still breaking apart. The central Atlantic Ocean, born from the rifting that had triggered the camp eruptions, was widening by about ½ an inch per year. That does not sound like much, but over millions of years, ½ inches become hundreds of miles. New oceanic crust was forming along the mid-Atlantic ridge, hot rock rising from the mantle and solidifying as it spread outward. Sea levels were rising as the new ocean basin filled with water, and shallow seas began to flood the edges of continents, creating extensive coastal environments rich in nutrients and warmth. These shallow marine environments became havens for recovering life, warm, sunlit, full of the raw materials that organisms needed to rebuild. On land, the early Jurassic was when the fundamental patterns of the dinosaur age were being established. Food webs were forming that would persist, with modifications, for the rest of the period. Predator-prey relationships were developing between newly dominant dinosaurs and the animals they hunted. Herbivores were adapting to specific plant types, developing the teeth and digestive systems needed to process tough gymnosperm foliage.
The stage was being set. And perhaps most importantly, the early Jurassic was when dinosaurs proved they could succeed not just as survivors, but as the dominant land vertebrates. The extinction had given them an opportunity, and they took it, spreading across continents, diversifying into new forms, growing larger, becoming more specialized. By the end of the early Jurassic, there was no question about who ruled the land. The world of the Pseudosuchians was gone, and the age of dinosaurs had genuinely begun. But the early Jurassic was only the foundation. What came next, the middle and late Jurassic, spanning from about 175 million to 145 million years ago, was when the dinosaurs took that foundation and built something extraordinary on top of it. Something so large, so diverse, so ecologically dominant that it would define not just the Jurassic, but the image of prehistoric life in the human imagination forever. The giants were waking up, and the world was about to tremble under their feet. The geography of the early Jurassic tells a story of a planet being reorganized at its most fundamental level. Pangaea, still recognizable as a single landmass at the start of the period, was fragmenting along the lines that would eventually define the modern world. The rift that had spawned the camp eruptions was now a young ocean, the Proto-Atlantic, its waters shallow and warm, widening imperceptibly with each passing millennium. To the north, what would eventually become North America was beginning to pull away from Europe and Africa. The separation was not clean or sudden. Land bridges remained in some places, allowing animals to move between certain regions even as the ocean grew between them. To the south, the great land mass of Gondwana, the joined block of South America, Africa, India, Antarctica and Australia, still held together, though the stresses that would eventually tear it apart were already building. The coastlines of these landmasses were changing year by year, century by century, as rifts widened and seas flooded into the gaps. For the animals living through this transition, the geological drama was invisible. A sauropod browsing on conifers in what would become Tanzania had no awareness that the ground beneath it was drifting. A theropod hunting along a riverbank in what would become Colorado did not know that the Atlantic was growing somewhere far to the east. The changes happened too slowly for any individual life to perceive. But over millions of years, those changes accumulated until the world looked fundamentally different. New coastlines meant new habitats. Where rifts had opened and seas had flooded in, shallow marine environments appeared. Warm, nutrient-rich waters where life could flourish. Estuaries formed where rivers met these new seas, creating brackish zones rich in organic material. Sandy beaches stretched along some coasts, while rocky cliffs dominated where rifting had created steep edges. Each new type of coastline brought new opportunities for organisms to exploit. The separation of land masses also began to create the conditions for divergent evolution. As populations of dinosaurs and other animals became isolated on different continents, they evolved independently, adapting to local conditions and developing features that distinguished them from their relatives on other land masses. This process was slow in the early Jurassic, when connections between continents still existed and animals could still move between some regions. But it would accelerate as the breakup continued, eventually producing the regional faunas that characterized the late Cretaceous. Different dinosaurs on different continents, each shaped by the unique conditions of its particular landmass. The rivers of the early Jurassic world were the arteries that sustained life. They carried water from highland areas where rainfall collected down through valleys and plains to the growing seas. Along their banks, the densest vegetation grew, conifers reaching their tallest, ferns spreading their widest, cycads clustering in the filtered light. Animals concentrated near rivers because that was where the water was, and where the water was, the food was richest. Trackways preserved in ancient river sediments show heavy traffic, sauropods crossing at fords, theropods following the banks in search of prey, smaller animals darting between the cover of riverside vegetation. The lakes that formed in rift valleys were important habitats as well. Some of these lakes were enormous, filling the long, narrow depressions left by the stretching crust. Their waters reflected the forests around them, and their shores attracted the same diversity of life that modern lakeshores do. Herbivores coming to drink, predators following them, insects swarming over the water, amphibians breeding in the shallows. The sediments deposited at the bottoms of these lakes accumulated over millions of years, building up layered records of the ecosystems that surrounded them. Records that paleontologists mine today for the fossils and environmental information they contain. And through all of this, the rifting, the flooding, the erupting, the growing, the moving, the dinosaurs continued their expansion. Each generation spread a little farther, filled a few more niches, grew a little larger. The empty world that the Triassic-Jurassic extinction had created was filling up, niche by niche, species by species, with the animals that would define the next 135 million years. Before we meet the giants, it is worth pausing to understand the world they lived in, because the dinosaurs did not exist in a vacuum. They were shaped by their environment as much as they shaped it, and the Jurassic environment was unlike anything on Earth today. The planet was a greenhouse, not in the gentle metaphorical sense of a warm spring day. The Jurassic Earth was operating under a fundamentally different climate regime than the one you know. Carbon dioxide levels in the atmosphere were perhaps 4 to 5 times higher than pre-industrial levels. There were no permanent ice caps at either pole. Global average temperatures were significantly higher than today, and the difference between the warmest and coolest regions was smaller than what you experience now. Warmth extended from the equator toward the poles, and forests grew in places where today you would expect nothing but ice and tundra. Imagine Antarctica without ice. Instead of the frozen continent you know from photographs, picture it covered in forests of conifers and ferns, sustaining animals, breathing with life under a sky that never froze. Imagine the Arctic Circle, not as a barren expanse of white, but as a cool, forested region where plants grew slowly through long summer days, and animals browsed on vegetation that survived the polar night. These images seem impossible because they are so far from current conditions, but in the Jurassic, they were reality. The absence of polar ice meant that sea levels were higher. Water that is locked in ice caps today was liquid and in the oceans, and those oceans spread farther inland than they do now. Shallow seas covered parts of the continents, creating coastlines where marine and terrestrial ecosystems met and mixed. These shallow epicontinental seas were full of nutrients, supporting coral reefs, shellfish, fish, and marine reptiles. They also provided hunting grounds for pterosaurs and other animals that lived at the boundary between land and water. The higher sea levels meant that many continental interiors were less isolated from the moderating influence of the oceans. Moisture could reach farther inland. Rainfall was more abundant in many regions. The combination of warmth, moisture, and elevated carbon dioxide created conditions where plants could grow with extraordinary efficiency. Photosynthesis, the process by which plants convert sunlight and carbon dioxide into energy, works better when there is more carbon dioxide available. The forests of the Jurassic were, in many places, more productive than forests today, growing faster and denser, generating more biomass per acre. This abundance had cascading effects through the entire ecosystem. More plant growth meant more food for herbivores. More herbivores meant more food for predators. The greenhouse climate was not just a setting for the Jurassic drama, it was the engine that powered it. Without the warmth, without the elevated carbon dioxide, Without the resulting explosion of plant life, the sauropods could never have grown to the sizes they reached.
You simply cannot maintain a body weighing 50 or 70 tons on sparse vegetation. You need endless forests, endless ferns, endless cycads, and the Jurassic greenhouse provided exactly that. The climate also shaped how animals distributed themselves across the planet. With warmth extending toward the poles, animals were not confined to narrow bands of habitability the way they might be in colder periods. Forests reached into high latitudes, allowing herbivores to spread far north or south. Migration patterns were different from what you might expect today. Animals could range across wider territories without hitting walls of cold that would stop them.
This broader distribution is reflected in the fossil record. Similar dinosaur species have been found across vast distances, from what is now North America to Africa to Asia, suggesting that in the Jurassic, the world was more ecologically connected than it would be in later periods, when continents had drifted farther apart and climate zones had sharpened. Storms were part of this greenhouse world, and they were powerful. Warm oceans fueled weather systems similar to modern hurricanes and cyclones, but likely more frequent and more intense in some regions. These storms brought torrential rains that swelled rivers, flooded plains, and reshaped coastlines. Lightning ignited vegetation, starting fires that burned patches of forest and created mosaics of regrowth, cleared areas where ferns rushed in first, followed by cycads, then conifers, rebuilding the forest step by step. The cycle of storm, fire, and renewal was constant, and animals adapted to it. Some fled to higher ground during floods. Others waited out storms in dense forest. Still others followed the fires, feeding on the tender new growth that sprang up in burned areas. Seasons existed, but they looked different than the ones you know. Instead of winter bringing ice and snow, seasons in the Jurassic were defined more by changes in rainfall. Monsoon-like cycles brought heavy rains to some regions, followed by months of relative dryness. These wet-dry cycles profoundly affected plant and animal life. Ferns and cycads flourished during rainy periods. During drier months, vegetation became scarcer, and herbivores had to travel farther to find food. The migrations of sauropod herds may have followed these seasonal rhythms, moving across valleys and plains in search of the next flush of growth. Volcanic activity was never far away. Pangaea was still splitting apart, and the rifts produced eruptions that released gases and ash into the atmosphere.
These eruptions were smaller than the camp event that had ended the Triassic, but they were ongoing, a constant background of geological activity that shaped local landscapes, fertilized soils with volcanic minerals, and occasionally disrupted ecosystems. Earthquakes shook the ground as tectonic plates shifted. New coastlines appeared as seas widened. Mountains rose along rift margins, redirecting winds and creating rain shadows. The Earth was in constant motion, and life had to keep up. The oceans of the Jurassic were as dynamic as the land. The Tethys Ocean, which lay between the northern and southern halves of the breaking supercontinent, was warm, shallow, and biologically rich, a cradle of marine life. Coral reefs expanded along its margins, building complex structures that housed fish, mollusks, crustaceans, and invertebrates of every description. The reefs acted as hotspots of biodiversity, just as modern reefs do. Above them, marine reptiles hunted. Ichthyosaurs, shaped for speed. Plesiosaurs, with long necks and powerful flippers. And the formidable pliosaurs, apex predators with massive heads and teeth as long as bananas. The New Atlantic was still narrow, but growing, its waters beginning to establish the circulation patterns that would eventually make it one of the most important ocean basins on Earth. Currents carried heat from the tropics toward higher latitudes, helping maintain the even global warmth. Nutrients transported by those currents supported plankton growth, which fed fish, which fed larger predators, building food chains from the bottom up. This was the world the giants inherited. Warm, wet, volcanically active, teeming with plant life, connected by shallow seas and split by growing oceans. A world where the conditions aligned to support life at scales that had never been seen before and have never been seen since. The stage was set. The greenhouse was running. The forests were growing. And somewhere in those forests, the sauropods were beginning to grow as well. Their necks were lengthening. Their bodies were expanding. Their legs were thickening into pillars that could support weights that seem impossible until you understand the world that made them possible. The world was not merely warm. It was warm in a way that changed everything about how life operated. To understand the Jurassic properly, you need to feel this warmth as something more than a number on a thermometer. It was the medium in which every creature existed. The invisible hand that shaped every forest, every coastline, every animal that walked or swam or flew. If you could stand in a Jurassic forest, the first thing you would notice is the air. It would feel heavy. Not oppressively so, but noticeably. Thick with moisture, warm against your skin even in the shade. Breathing would feel different. Each inhalation would carry more humidity than you are used to, and the temperature would sit in a range that made sweat cling rather than evaporate. Under the conifers, where the canopy blocked direct sunlight, the air would be cooler and damper, filled with the smell of resin and wet earth. Step into a clearing, and the warmth would press against you, immediate and enveloping, the sun pouring heat onto the ground with an intensity that only the nearby shade could temper. The sounds of this world would be everywhere. Insects humming in continuous waves, their buzzing rising and falling as you moved through the forest. Frogs croaking near streams, filling the lower register with rhythmic pulses. Small reptiles rustling in the leaf litter, and beneath all of that, a deeper layer of sound. The distant, resonant calls of large animals, carried through humid air that held sound better than dry air does. Sauropods communicating across miles, predators growling in the undergrowth, the crack of a branch as something enormous pushed through the trees far away. The smells would be unlike anything in your experience. No flowers existed to perfume the air. Instead, the dominant sense would be resin from conifers, the damp green smell of ferns, the mineral tang of volcanic soil, and the rich, loamy odor of decaying plant matter. Near water, the smell of mud and algae. Near volcanic areas, the faint bite of sulfur. The Jurassic had its own atmosphere, dense with organic compounds and moisture. A world that you would experience through your lungs and your skin, as much as through your eyes. The Tethys Ocean deserves special attention here because it was one of the most important bodies of water in the Jurassic world. Wedged between the northern and southern halves of the breaking supercontinent, the Tethys was warm, shallow, and biologically productive beyond anything in the modern oceans. Its coastlines stretched for thousands of miles, and along those coastlines, coral reefs flourished in complex structures that housed fish, mollusks, crustaceans, and invertebrates of every description. These reefs were not like the coral reefs you might picture from documentaries about the modern tropics. The corals were different species, sharing space with sponges and algae that helped build the reef structures. But their function was the same. They created three-dimensional habitats where life could pack itself in at extraordinary density. Fish darted between coral branches. Crustaceans scuttled along the reef floor. Ammonites hovered nearby, their coiled shells catching the light as they drifted on gentle currents. And above the reefs, the shadows of marine reptiles passed. Ichthyosaurs hunting with speed, plesiosaurs gliding with their long necks extended, scanning for prey. The reefs also served as nurseries.
Many marine species used them as safe places for their young, sheltering juveniles in the complex structures until they were large enough to venture into open water. This function made the reefs critical not just for the species living on them, but for the broader marine ecosystem. They were engines of biodiversity, concentrating life in ways that open ocean could not match. Beyond the reefs, the open oceans of the Jurassic were highways for migration and dispersal. Warm currents carried nutrients across vast distances, supporting plankton blooms that fed fish, that fed larger predators, building food chains from the bottom up. Ammonites, those spiral-shelled cephalopods, were everywhere, so abundant and so rapidly evolving that their fossils now serve as one of the most important tools for dating Jurassic rocks. In their own time, they were simply one of the most common and most successful groups of marine animals, filling the oceans with their drifting forms, feeding on plankton and small animals, and being fed upon in turn by everything larger. The interaction between land and sea was constant and vital. Rivers carried nutrients from forests and prairies into the oceans, feeding plankton blooms near coastlines. These nutrients supported food chains that extended from microscopic algae all the way up to marine reptiles the size of buses. Pterosaurs soared above the coastal waters, diving to catch fish or scavenging along shores. Dinosaurs walked the beaches. Their footprints have been found preserved in fossilized shoreline sediments, evidence of the constant traffic between the terrestrial and marine worlds. This interconnection meant that changes in one system rippled into the other. A drought on land that reduced river flow could diminish nutrient delivery to coastal waters, affecting plankton, affecting fish, affecting the marine reptiles that hunted them. A volcanic eruption that dumped ash into the sea could kill local marine life, but also fertilize the water with minerals, triggering blooms once the ash settled. The Jurassic world was a web, and every strand in that web was connected to every other strand. The plants of the Jurassic deserve more attention than they usually receive, because without them, nothing else in this story would have been possible. They were the foundation of the entire Mesozoic world, and the way they covered the planet was unlike anything you are familiar with today. The most striking absence was grass. No meadows existed. No prairies of waving grass stretched beneath open skies. Instead, the ground was covered by ferns, wide mats of green spreading across lowlands, floodplains, and the open spaces between forest stands. These fern prairies were not uniform. Some were made of small, low-growing species that hugged the soil, their fronds overlapping until barely any bare ground remained. Others were filled with taller ferns, reaching waist height or higher, forming dense stands that an animal would have to push through to cross. Moving through a fern prairie would have been like wading through a sea of green leaves, each frond brushing against your legs, parting ahead of you and closing behind. These fern prairies were essential to the ecosystem in ways that went far beyond providing ground cover. Large herbivores grazed on them,
stripping fronds with their beaked mouths or broad teeth. Smaller dinosaurs darted into them for food and shelter. Mammals and lizards used the low vegetation as cover from predators. Insects thrived in the moist, protected environment between the fronds, feeding on plant tissue and laying eggs on the undersides of leaves.
The fern prairies were dining halls and shelters and nurseries, all wrapped into one continuous green carpet. Beneath the canopy of the great conifer forests, ferns dominated the understory as well. Where enough light filtered through the branches above, ferns grew in continuous layers, creating a second forest beneath the first. This understory was a world of its own, cooler, damper, filled with the smell of soil and decomposing vegetation. Smaller animals moved through it, largely hidden from view, and predators hunting in the forest had to rely on sound and smell more than sight to find prey concealed in the dense foliage below. The resilience of ferns came from their simple but effective reproductive strategy. By producing vast numbers of spores that could be carried by wind across enormous distances, they could colonize disturbed ground faster than almost any other plant.
After fires, floods, or volcanic eruptions, ferns were typically the first plants to return, their spores germinating in the ash and bare soil, their fronds unfurling within weeks, covering blackened ground in green, before any other vegetation could establish itself. This pioneering ability made ferns the first responders of the Jurassic botanical world, the plants that stabilized soils and created conditions for slower-growing conifers and cycads to follow. Fire was a regular part of the Jurassic landscape, and its interaction with the forests shaped the appearance of the world in important ways. Lightning from the frequent storms ignited vegetation, burning patches of forest and fern prairie. Some conifers were adapted to survive fire. Their thick bark protected their trunks, and their cones could open after being heated, releasing seeds into freshly cleared ground where competition was low.
After a fire, the succession was predictable. Ferns first, covering the ash in green, then cycads and horsetails filling the gaps, then conifers rising above them, rebuilding the canopy over decades. Animals responded to fire as well, fleeing the flames and then returning to graze on the tender new growth that sprang up in burned areas. Fire was destructive in the short term, but creative in the long term, maintaining a mosaic of habitats at different stages of regrowth that supported a wider range of species than a uniform, unbroken forest could. The cycads filled a particular niche in this world. With their stout trunks and crowns of stiff, palm-like leaves, they grew in open areas and in the gaps between conifers. They reproduced using cones rather than flowers, and their seeds were encased in tough shells that could survive being swallowed and pass through the digestive systems of large herbivores, a strategy that helped them spread across the landscape. Dinosaurs fed on cycads, tearing at their leaves and occasionally consuming their cones. But cycads were resilient plants, capable of regrowing after being grazed. Their toughness made them a staple food source for the great herbivores, even though their nutritional value was modest compared to the lush ferns that grew nearby. Horsetails, those strange, segmented plants with hollow stems topped with spore-bearing cones, grew in dense stands wherever the ground was wet. In the Jurassic, some horsetails reached heights that dwarfed their modern descendants, up to 30 feet in some estimates, forming tall, straight thickets along the edges of lakes and rivers. They stabilized soils against erosion, provided cover for small animals, and added their own distinctive silhouette to the wetland landscapes. Walking along a Jurassic river, you would have passed through stands of horsetails that rose above your head, their hollow stems swaying slightly in the breeze, their cone-like tips releasing spores that drifted on the air. Together, these plants built the world that the dinosaurs lived in. They provided the food, the shelter, the oxygen, the soil stability, and the microhabitats that every animal depended on. When a sauropod pushed through a conifer forest, knocking down trees and opening gaps in the canopy, it was not just feeding. It was reshaping the plant community, creating spaces where ferns could rush in, where cycads could establish, where the mosaic of the forest was maintained in the dynamic, constantly shifting state that supported the maximum diversity of animal life. The plants were the stage, the script, and the supporting cast of the Jurassic drama. Every tooth and every claw and every bone that fills museum halls today owed its existence to the green world that sustained it. The forests carried the weight of the giants, and in return, the giants shaped the forests. That partnership, quiet and constant, was the engine that drove the entire age. The soundscape of the Jurassic was as much a part of the world as the forests and the oceans, and if you could stand quietly in any environment of that age, you would hear a planet that was never silent. Sound was essential to survival, for communication, for warning, for hunting. And every animal contributed its own voice to a chorus that shifted with the time of day, the season, and the landscape. Start with the forests. Under conifers, stretching 100 feet or more, the wind moved through branches with a steady hiss, a sound not unlike modern pine forests in a breeze. Cycads and ferns swayed at ground level, adding a softer rustle. Insects provided the constant baseline, a humming that rose and fell as individual beetles, flies, and dragonflies passed by. Near streams, frogs added rhythmic calls that carried through the understory, and somewhere in the leaf litter, the quick scratch of a mammal's claws on bark or a lizard's feet on fallen leaves added brief, sharp sounds to the softer background. The larger animals had voices that carried. Sauropods, with their enormous bodies and long necks, almost certainly produced deep, resonant sounds. Low-frequency rumbles that could travel for miles, vibrating through the ground and the air simultaneously. Modern elephants communicate using infrasound, frequencies too low for human ears to detect easily, but powerful enough to be felt as much as heard. Sauropod calls were probably similar. Deep, thrumming vibrations that a human observer would feel in the chest and the soles of the feet before consciously hearing them. A herd of sauropods, moving across a plain, would have produced a constant, low drone of communication, coordinating movement, signaling the location of individuals, maintaining the cohesion of the group. Stegosaurs may have added deeper grunts or bellows, warning predators or communicating with mates. Their tail spikes, the thagomizer, may have produced sound when swung against the ground in defensive display, a heavy thud that would carry through the earth. Ornithopods, the smaller plant-eaters, could have produced higher-pitched calls, chirps or honks that cut through the forest sounds. Some dinosaurs had complex nasal cavities that in later relatives like the hadrosaurs were used to produce resonant, trumpet-like calls. In the Jurassic, those structures were less developed, but sound was clearly an important part of dinosaur life. Predators had their own voices. Allosaurus probably did not roar the way movies depict. The reality was likely a mix of low growls, guttural bellows, and hissed warnings. Modern crocodilians produce deep rumbles by vibrating air sacs in their throats, and large theropods could have done something similar. The sound of an Allosaurus announcing its territory or warning arrival might have echoed through valleys, shaking the air with a vibration that smaller animals would have felt as a signal to freeze, to hide, to become very still and very quiet. Along coastlines, the soundscape blended terrestrial and marine elements.
Waves crashed or lapped against shorelines. Pterosaurs screeched as they circled overhead, their sharp calls cutting through the rush of water. Marine reptiles surfaced with gasping breaths, sometimes producing low calls that carried underwater. The wind off the ocean carried salt and moisture, and the sounds it brought shifted with the weather. Gentle during calm periods, roaring during storms.
Night changed everything. When the large dinosaurs quieted, the smaller creatures grew louder. Insects reached a crescendo, their buzzing filling the darkness. Frogs chorused with an intensity that drowned out everything else near water. Mammals rustled in underbrush, their small sounds amplified by the stillness around them. And in that darkness, every sound carried meaning. The snap of a twig could signal a predator. The splash of water could mean a large animal was near a stream. Silence itself was a warning. When the usual background suddenly stopped, it meant that something dangerous had been detected, and every creature within earshot froze, listening, waiting. The daily rhythm of sound followed the rhythm of life. Dawn brought the stirring of insects and the first calls of waking animals. Morning was the busiest time, with herbivores calling to gather herds and predators beginning their hunts. Afternoon storms added thunder that rolled across valleys, shaking forests and drowning out animal voices. When the storm passed, the calls resumed, often louder in the cooler, cleaner air. Evening brought the transition from day-active to night-active species, a changing of the guard marked by a shift in the soundscape from deep rumbles and sharp calls to high-pitched chirps and buzzing. This was the pulse of the Jurassic world. Never silent, always communicating, always alive with information carried on waves of sound through humid, heavy air. The volcanoes of the Jurassic were not occasional events. They were a constant feature of a planet pulling itself apart. As Pangaea continued to fracture, rifts opened along the lines where continents were separating, and along those rifts, magma rose to the surface with a regularity that shaped landscapes, climates, and the lives of every creature in the vicinity. Imagine standing near one of these rift valleys in the Middle Jurassic. The ground might tremble faintly beneath your feet, a vibration so subtle you would dismiss it if you were not paying attention. Then a crack opens in the earth, glowing with orange light as magma pushes upward. Over hours or days, the eruption builds, fountains of lava rising, rivers of molten rock flowing downhill, igniting vegetation, forcing animals to scatter. Ash clouds spread upward, turning the sky dark, blocking the sun. For miles around, the world changes. Forests vanish, rivers boil. The air fills with the smell of sulfur and the sound of splitting rock. And yet, these eruptions were also creative forces. The lava that destroyed forests in the short term created new land and new soils in the long term. Volcanic rock weathers quickly in warm, humid conditions, breaking down into mineral-rich soil that supports vigorous plant growth. Within decades of an eruption, ferns would be spreading across the cooled lava, their roots breaking the rock into something that could hold water and nutrients. Cycads would follow, then conifers, rebuilding the forest from the ground up. Animals would return as soon as the vegetation allowed, browsing on the fresh growth that volcanic soils made possible. The gases released by these eruptions fed the greenhouse climate that defined the Jurassic. Carbon dioxide from volcanic vents entered the atmosphere and trapped heat, maintaining the warm, ice-free conditions that allowed forests to extend toward the poles and sauropods to grow to sizes that would be impossible in a cooler world. The volcanoes were not enemies of life. They were part of the system that sustained it, destructive when they erupted, but essential in the long run for the climate stability and soil fertility that the entire ecosystem depended on. Earthquakes accompanied the rifting too.
As tectonic plates shifted, sudden jolts cracked the land, altered rivers, and triggered landslides. Herds of dinosaurs may have felt the ground shake beneath them and scattered instinctively, the way modern animals react to tremors. Coastal areas could shift during seismic events, changing habitats overnight. In regions where rifting was most active, earthquakes were frequent enough that they became part of the background of life, a regular reminder that the earth beneath was never truly still. The interplay between volcanic activity and the rest of the ecosystem was constant and complex. Ash falling on forests could smother small plants and clog streams. But the same ash, once settled and broken down by rain, enriched soils with minerals that promoted growth. Lava flows that dammed rivers created lakes behind them, and those lakes became habitats for fish, amphibians, and the insects that swarmed over still water.
Over millions of years, the sediments deposited in volcanic lakes preserved fossils with extraordinary detail, giving paleontologists windows into the ecosystems that existed around these restless geological features. The movement of continents continued throughout the Jurassic and into the Cretaceous, never pausing, never stopping. Mountains rose along rift margins, valleys formed where the crust was stretching thin. New coastlines appeared as seas widened between drifting land masses. And through all of this geological upheaval, life adapted, shifting, migrating, evolving, always keeping pace with a planet that never sat still. The dinosaurs did not live on a stable stage. They lived on a stage that was constantly being rebuilt beneath their feet, and their ability to adapt to that constant change was one of the reasons they lasted as long as they did. But even the most adaptable organisms have their limits, and the changes that were coming, not from below, but from above, would test those limits beyond anything the Jurassic or even the Cretaceous could prepare them for. The age of giants was about to begin, and once it started, it would not stop for 50 million years. There is something fundamentally astonishing about the sauropods, something that goes beyond mere size and touches on the limits of what biology can achieve. These were animals that weighed as much as 10 or 15 African elephants, animals that stood as tall as a 4-story building, animals that measured from nose to tail tip the length of a basketball court. And they did all of this on land, where gravity pulls relentlessly downward and where every pound of body mass must be supported by legs, powered by muscles, and nourished by a circulatory system that somehow managed to pump blood up necks stretching toward the sky like organic cranes.
The question that has fascinated paleontologists for over a century is straightforward to ask and extraordinarily complex to answer. How did sauropods get so big? The answer, it turns out, involves almost everything. Their breathing, their eating, their growing, their bones, their reproduction, even the atmosphere they breathed, and the plants they consumed. Gigantism in sauropods was not the result of any single adaptation. It was the result of many adaptations working together, each one enabling the next, building a body plan that could exist at a scale no land animal has matched before or since. Start with their breathing. Sauropods, like all dinosaurs, almost certainly had a system of air sacs connected to their lungs, the same kind of system that modern birds possess. In birds, air flows through the lungs in one direction, in through one set of passages, through the gas exchange surfaces, and out through another set.
This means that fresh, oxygen-rich air is always passing over the lung surfaces, even during exhalation. Mammals, by contrast, breathe in and out through the same passages, which means the air in their lungs is always a mixture of fresh and stale. The avian system is more efficient, extracting more oxygen per breath. For sauropods, this efficiency was essential. A heart pumping blood up a neck 10 or 50 feet long needs all the oxygen it can get, and a bidirectional lung system would have struggled to provide it. The air sacs served another purpose as well. They invaded the bones. The vertebrae of sauropods, those enormous column-like bones that supported their necks and tails, were not solid. They were riddled with air spaces, pockets, and chambers connected to the respiratory system that reduced weight without sacrificing strength. Pick up a bird bone sometime and notice how light it is.
That lightness comes from the same principle. Air-filled bones that provide structural integrity with a fraction of the weight of solid bone. In sauropods, this pneumatization was critical. Without it, their skeletons would have been too heavy for their muscles to move. The air sacs literally made gigantism possible by keeping the scaffolding light enough to function. Then there was the matter of eating. A sauropod needed to consume hundreds of pounds of vegetation every single day just to maintain its enormous body. Their long necks gave them access to food that no other animal could reach. The tops of conifer trees, the highest cycad crowns, vegetation that was simply out of range for anything else. But different sauropods used their necks in different ways. Brachiosaurus carried its neck high, like a giraffe, browsing at levels far above the ground. Its front legs longer than its back legs, giving its body a distinctive upward slope. Diplodocus, by contrast, probably held its neck more horizontally, sweeping it in wide arcs across the ground to harvest ferns and low vegetation over a large area without moving its body. Apatosaurus had a more robust build, its body low and powerful, suited to stripping tough vegetation in bulk. This partitioning of food resources is important because it allowed multiple sauropod species to coexist in the same ecosystems. They were not all competing for the exact same plants. They were dividing the available food among themselves, each species taking a different slice, the way different birds in a modern forest feed at different heights. High browsers, low sweepers, and mid-level feeders could share a landscape because their feeding strategies did not overlap completely. The teeth of sauropods reflected their feeding habits. Most had teeth suited for stripping and grabbing, pencil-shaped or spatula-shaped, designed to rake leaves from branches rather than chew them.
Sauropods did not grind their food the way mammals do. Their teeth were for harvesting, not processing. The actual breakdown of plant material happened inside their massive guts, where long digestive tracts and microbial fermentation extracted energy from tough, fibrous vegetation. Many paleontologists believe sauropods swallowed stones called gastroliths, which helped grind food in their stomachs, much as modern birds use grit in their gizzards. Their growth rates were remarkable. Fossil evidence shows that sauropods hatched from eggs no larger than a football. To reach lengths of 65 to 100 feet and weights of 50 or more tons, they had to grow rapidly, putting on tons of weight in just a few decades. Bone studies show growth rings that indicate many sauropods reached near adult size within 15 to 20 years, growing at rates that would astonish anyone familiar with modern large animals. An elephant takes decades to reach full size. A sauropod compressed that journey into a fraction of the time, driven by metabolisms that demanded constant intake and converted food into body mass with remarkable efficiency. This rapid growth was itself a survival strategy. A young sauropod, freshly hatched and no bigger than a house cat, was vulnerable to every predator in its world. The faster it grew, the sooner it reached a size where most predators could not touch it. A full-grown sauropod was nearly invulnerable. Nothing alive in the Jurassic had the ability to bring down a healthy adult Brachiosaurus or Diplodocus. Their size was their armor, their primary defense against a world full of large, aggressive theropods. The impact of sauropods on their environment was profound. Moving through forests, they knocked down trees, opened gaps in the canopy, and reshaped the vegetation. Their feeding created pathways and clearings. Their dung fertilized the soil, spreading nutrients and seeds across vast areas.
Their migrations, following the seasonal rhythms of rainfall and plant growth, ensured that ecosystems were constantly disturbed and renewed. In a real sense, sauropods were ecosystem engineers. They did not simply live in the Jurassic landscape, they made it. Fossils suggest that sauropods travelled in groups. Trackways preserved in ancient floodplains show parallel lines of footprints, indicating herds walking together. These trackways sometimes show adults and juveniles side by side, suggesting that protection of the young was part of their social strategy. A herd of sauropods moving across a plain must have been an awe-inspiring sight, the ground trembling beneath their combined weight, their deep calls resonating through the air, their necks swaying above the treetops like masts on ships. Imagine standing on a Jurassic floodplain and seeing them approach. First, you would feel it, a tremor in the ground, rhythmic and heavy. Then you would hear them. Low, resonant sounds that you would feel in your chest more than hear with your ears. Infrasound, similar to what modern elephants use to communicate across distances. Then the shapes would resolve through the trees, necks rising above the canopy, bodies massive and unhurried, tails trailing behind them in long, steady arcs. They would pass you without concern. You would be too small to threaten, too small to notice. To them, you would be an insect, invisible against the vastness of their world. The sauropods are often the first thing people think of when they picture the Jurassic, and for good reason. They were the defining animals of their age, the largest land creatures the Earth has ever produced, built by evolution to take advantage of a greenhouse world where plants grew without end and warmth enveloped the entire planet. Their bones, found on every continent, testify to their success. Their trackways, preserved in stone, record their passage across landscapes that have long since vanished. And their sheer scale challenges everything we think we know about what is possible for a living thing. But sauropods were not alone. The Jurassic world was filled with other dinosaurs, other creatures, other dramas playing out at every scale. And among the most important of those dramas was the constant, relentless interaction between the herbivores that fed on the forests and the predators that hunted them. Because wherever there are giants, there are also those who hunt them. And the hunters of the Jurassic were formidable in their own right. If the sauropods were the rulers of the Jurassic land through their size and abundance, the predators were the forces that tested them, shaped their behavior, and kept the balance of the ecosystem in constant motion. Among these predators, Allosaurus and its relatives stood as the dominant hunters of their age. They were not the only carnivores, but they were among the largest, most adaptable, and most widespread. Allosaurus itself is the most famous representative of Jurassic predation. Its fossils have been found in enormous numbers, especially in North America, where entire bone beds hold the remains of dozens of individuals. That abundance tells us something immediately. Allosaurus was not a rare specialist. It was common and successful, filling the role of top predator across vast regions for millions of years. An adult Allosaurus reached 30 to 40 feet in length, with strong hind legs, a long tail for balance, and a skull that was large but relatively light, built with openings that reduced weight while maintaining structural strength. Its teeth were serrated and recurved, designed not for crushing bone the way a later tyrannosaur would, but for slicing flesh. Combined with powerful neck muscles, those teeth could deliver slashing bites that opened deep wounds, weakening prey over time, rather than killing with a single strike. What made Allosaurus particularly effective was the combination of its tools. Strong hind limbs gave it speed and agility. 3 sharp claws on each hand could grip and slash. Its jaws could open wide enough to deliver devastating bites to flanks and throats. Allosaurus was built for a style of hunting that relied on inflicting damage and then following the weakened prey until it could no longer resist. Evidence from the fossil record supports the idea that Allosaurus regularly attacked sauropods.
Bite marks on sauropod bones match the teeth of Allosaurus, showing that they at least fed on these giants, whether through active hunting or scavenging. The sheer size of an adult sauropod would have made a direct kill difficult, but a young or injured individual would have been vulnerable, and Allosaurus did not have to work alone. While the question of whether they hunted in coordinated packs remains debated, fossil accumulations suggest that multiple individuals sometimes gathered around kills, possibly tolerating each other's presence in areas where prey was abundant, the way modern crocodiles or Komodo dragons will share large carcasses. The interactions between predator and prey were constant and shaped the evolution of both sides. Imagine a herd of stegosaurs moving slowly across a floodplain, browsing on ferns. The adults carried their distinctive tail spikes, the thagomizer, 4 pointed spines capable of inflicting lethal wounds. A puncture wound matching a stegosaur tail spike has been found in an Allosaurus vertebra, showing that these weapons were not just for display. They were used, and they were effective. An Allosaurus circling a herd of stegosaurs had to calculate whether the risk was worth the reward.
Attacking a healthy adult meant facing those spikes.
The safer option, always, was to target the young or the weak. Smaller theropods filled the gaps beneath the Allosaurus. Some were no larger than a turkey, quick and nimble, hunting insects, lizards, and early mammals in the understory. Others were mid-sized, targeting smaller herbivores or the eggs and young of larger dinosaurs. The layering of predator sizes created a balanced ecosystem where every niche was occupied. Large predators at the top, small ones at the bottom, and a gradient in between. Predators also faced dangers of their own. Allosaurus skeletons frequently show healed injuries, broken ribs, bitten limbs, infected wounds. Hunting was dangerous work, and not every attempt succeeded. Prey fought back. Rivals competed for kills and territory. Infections from wounds could weaken or kill. The life of a Jurassic predator was not one of effortless dominance.
It was a life of constant risk,
where every meal carried the possibility of injury, and every injury could be the last. Scavenging played a role too. A carcass left by flood, disease, or another predator was a valuable resource that required no risk to obtain. Allosaurus almost certainly scavenged when opportunities arose, and the competition around a carcass could be intense. Multiple predators converging on the same kill, smaller scavengers darting in to steal morsels, insects arriving in clouds to consume what was left, the Jurassic equivalent of what plays out around a kill on the African savanna today. In the oceans, predation followed its own rules. Ichthyosaurs were the speedsters, dolphin-shaped, fast and agile, hunting fish and squid with large eyes that gave them excellent vision even in dimmer waters. Plesiosaurs used a different strategy, their long necks allowing them to strike into schools of fish with sudden, darting movements, while their broad bodies held position.
And then there were the pliosaurs,
The apex predators of the Jurassic seas, with massive skulls, short necks, and jaws filled with teeth that could crush bone. Some pliosaurs grew enormous, their heads alone the size of a car, their bite force among the strongest of any marine animal that has ever lived. They hunted anything they could catch, including other marine reptiles, making the Jurassic oceans a place where even large predators had to watch for larger ones. Above the water, pterosaurs soared on wings of membrane stretched between elongated fingers. They were the first vertebrates to achieve powered flight, and by the Jurassic, they had diversified into many forms, from small insect-eating species to larger fish-eaters that dipped down to the surface to snatch prey from shallow waters. Pterosaurs were not dinosaurs, though they were close relatives, and their mastery of the skies added another dimension to the Jurassic world. Every ecosystem had its aerial component, creatures that moved through the air above the forests and the seas, hunting, scavenging, and connecting the terrestrial and marine worlds.
And this brings us to one of the most remarkable subplots of the Jurassic story, because the skies were about to welcome a new kind of flyer. Not a pterosaur with its membrane wings and elongated fingers. Something different, something smaller, feathered and clumsy, testing the air with wings it had only just begun to develop. The first birds were appearing, and their story begins not in the sky, but on the ground, among the very predators we have been talking about. But the Jurassic was not only a world of giants and predators. If you lowered your gaze from the towering sauropods and the stalking allosaurs, you would find a world teeming with smaller life. Creatures that filled every corner the giants could not reach, and that played roles just as vital in the functioning of the whole system. Mammals had been present since the late Triassic, surviving through the extinction that gave the dinosaurs their chance, and persisting through the Jurassic as small, secretive animals living in the shadows of their reptilian overlords. Most Jurassic mammals were about the size of a mouse or a shrew, built for speed, agility, and concealment. Their skeletons show adaptations for quick movement, digging, and climbing. Many were nocturnal, taking advantage of the night when the great dinosaurs were less active, slipping through the underbrush in the dark to hunt insects and avoid becoming prey themselves. Their teeth tell an important part of their story. By the Jurassic, mammals had already developed specialized dentition, incisors, canines, and molars adapted for different functions. This meant they could process food more efficiently than reptiles could, chewing insects, small vertebrates, or plant material with a precision that gave them more energy per mouthful. Their fur provided insulation, keeping body temperatures stable through cool nights. Their metabolisms were faster than those of reptiles, requiring them to eat more often, but giving them more energy for activity. These adaptations, warm-bloodedness, fur, specialized teeth, active metabolisms, were not evolved for the distant future. They were survival tools for the present, strategies that allowed small mammals to carve out niches in a world dominated by much larger animals. The mammals of the Jurassic were not trying to compete with sauropods or allosaurs. They survived by occupying spaces too small for dinosaurs to notice or care about. They hunted insects in the leaf litter, dug burrows for safety, raised young in hidden nests. Some could climb trees, scurrying through branches in search of food or escape. Others lived along riverbanks, feeding on aquatic invertebrates. Their diversity was already impressive, even though their size remained modest.
By avoiding direct competition with the dominant animals, they carved out safe zones in a world that would have crushed them if they had tried to grow any larger. Insects were even more numerous and even more essential. They had been around for hundreds of millions of years before the dinosaurs appeared, and by the Jurassic they included beetles, flies, dragonflies, wasps, and many other groups. Without flowering plants, their role as pollinators was less complex than it would become in the Cretaceous, but they were crucial as decomposers, predators, and prey. Beetles broke down dead wood, recycling nutrients back into the soil. Flies bred in organic matter, contributing to decomposition. Dragonflies hunted smaller insects in the air, their wings shimmering over wetlands. And most importantly, insects provided food for a vast array of other animals: birds, mammals, amphibians, reptiles, and even some dinosaurs depended heavily on insects as a primary food source. The air above a Jurassic wetland would have been thick with them. Clouds of dragonflies hovering, their wings beating fast enough to produce a constant shimmer. Beetles scurrying across decaying logs. Mosquito-like forms buzzing near water. The hum of insects was a constant background, a sound that never stopped, day or night. And that hum was the sound of the base of the food web, the foundation upon which everything larger rested. Amphibians added their voices to the chorus. Frogs had already appeared, and their calls echoed near ponds and streams just as they do today. Salamander-like creatures swam through clear water, hiding under rocks and feeding on insects and small fish. The humid greenhouse climate was perfect for amphibians, providing the water they needed for breeding and the warmth they needed for activity.
Their fossils appear in wetland deposits across the Jurassic world, showing that they were widespread and common, even if they never approached the size or prominence of the dinosaurs. Small reptiles were everywhere, lizards basking on warm rocks, darting after insects with quick, snapping jaws. Early relatives of crocodiles lingered near waterways. Turtles paddled in rivers and ponds, their shells offering protection from predators that might otherwise have taken them easily. Each of these groups added to the complexity of the ecosystem, creating a web of interactions that extended from the smallest insect to the largest sauropod. The importance of these small creatures becomes clear when you think about energy flow. Large herbivores consumed enormous quantities of plants, but their populations were limited by the amount of food available. Large predators were even fewer, constrained by the number of herbivores they could catch.
But insects, mammals, amphibians, and small reptiles existed in staggering numbers. They recycled nutrients, moved energy through food webs, and ensured that no resource went entirely to waste. Without them, the system would have collapsed. The giants depended on the tiny creatures just as much as the tiny creatures depended on the world the giants maintained. Imagine the daily rhythm of these smaller lives. As dusk settles over a Jurassic forest, the large dinosaurs grow quiet. The sauropods that spent the day browsing on treetops settle into a kind of stillness, their massive bodies radiating the heat they absorbed during the day. The theropods withdraw to wherever they rest, their hunting done or postponed until morning. And in the gathering darkness, another world comes alive. A small mammal emerges from its burrow, whiskers twitching, nose testing the air for the scent of predators.
It moves quickly, staying close to cover, heading for a patch of leaf litter where beetles are already active. A dragonfly makes its last pass over a pond before settling onto a fern frond. Frogs begin their evening chorus, filling the darkness with pulses of sound that carry through the humid air. A lizard, still warm from a day of basking, slips under a log and goes still. Each of these small acts is almost invisible against the backdrop of the Jurassic world. But together, they form the heartbeat of the ecosystem, the constant, quiet pulse of life that continued day and night, season after season, for tens of millions of years. The balance between predator and prey was one of the defining features of Jurassic and Cretaceous ecosystems, and it operated with a precision that kept the entire system stable for tens of millions of years at a time. For the giant sauropods, survival meant feeding almost constantly. Their enormous bodies required hundreds of pounds of vegetation each day, and their necks, tails, and digestive systems were all adapted to meet that demand. But eating that much meant moving across large areas, stripping vegetation from one region before shifting to another. This movement shaped entire landscapes, and it also exposed them to predators. An adult sauropod was nearly untouchable. Nothing alive had the ability to bring down a healthy Brachiosaurus or Diplodocus in its prime. But the young were vulnerable. Newly hatched sauropods, small enough to hold in two hands, had to survive years of growth before reaching a size that offered any real protection. During those years, predators took a constant toll. Herds formed partly to protect these juveniles, with adults circling around the young when danger approached, presenting walls of massive bodies and swinging tails to ward off attackers. Stegosaurs had a different strategy.
They could not outgrow predators the way sauropods did, but they could fight. Their tail spikes were genuine weapons. Fossil evidence includes an Allosaurus vertebra with a hole the exact size and shape of a stegosaur tail spike punched through it. That injury may have been fatal. The message was clear. Attacking a stegosaur came with real risk of death. Predators learned this, and the calculus of each encounter was always a balance between the potential reward of a meal and the potential cost of a fatal wound. Smaller herbivores relied on speed and alertness. Ornithopods could dash into cover or flee across open ground, using their lighter bodies and longer legs to outrun heavier predators. Some had sharp senses, large eyes for detecting movement, sensitive hearing for picking up the approach of danger. Their survival was measured in seconds during an attack, and every hesitation, every stumble could mean death. The predators faced their own challenges. Allosaurus skeletons are frequently marked with healed injuries, broken ribs, bitten limbs, infected wounds that speak of hunts gone wrong, of prey that fought back, of rivals that contested kills. Hunting was not effortless dominance. It was calculated risk, where each attempt could end in injury or death as easily as success. The bones of Jurassic predators tell a story of lives lived on the edge, bodies battered by the consequences of a profession that demanded violence and received it in return. Scavenging offered a safer alternative when it was available. A carcass left by flood, disease, or another predator provided nutrition without the risk of a hunt. But scavenging had its own competitions. Multiple predators converging on the same kill, smaller scavengers darting in to steal morsels, insects arriving in swarms to consume what was left. The hierarchy around a carcass was determined by size, aggression, and numbers, and disputes could be violent.
Weather added another variable to the balance. Droughts reduced water sources, concentrating animals around the remaining pools and making them vulnerable. Fossil bone beds in the Morrison Formation, the famous Jurassic deposits of Western North America, often represent catastrophic accumulations where many animals died together, probably during droughts, when water dried up and desperation drove them to take risks they would normally avoid. Floods were equally dangerous, sweeping away young and old alike, depositing carcasses in jumbled heaps that paleontologists find millions of years later. The system sustained itself because the rates balanced. Birth rates high enough to replace losses, food supplies abundant enough to support the chain from plants to herbivores to predators, disturbances frequent enough to prevent any one species from overwhelming the rest, but not so frequent that the entire system collapsed. This dynamic equilibrium, never static, always adjusting, but always persisting, kept the Jurassic ecosystem functioning for tens of millions of years, longer than any human institution, longer than any civilization, longer than the entire span of time that separates us from the first mammals. And the same principles operated in the Cretaceous, with different players, but the same underlying logic. Tyrannosaurus replaced Allosaurus at the top. Triceratops replaced Stegosaurus as the armored defender. Hadrosaurs replaced the earlier ornithopods as the abundant grazers. The cast changed, but the play continued, because the rules of predator and prey are not rules that belong to any particular era. They are rules that belong to life itself. The connection between dinosaurs and birds is one of the most beautiful stories in all of science, and it unfolds most clearly in the Jurassic.
Because the birds that fill your world today, every sparrow, every hawk, every penguin, are not merely related to dinosaurs. They are dinosaurs. Living, breathing, singing dinosaurs. Direct descendants of a lineage of small theropods that, during the Jurassic period, began experimenting with a structure that would eventually carry them into the sky. Feathers did not evolve for flight. That is perhaps the most surprising part of the story. The earliest feathers were simple filaments, hair-like structures that covered the bodies of small theropod dinosaurs, millions of years before any of them took to the air. These proto-feathers almost certainly evolved for insulation, a way to retain body heat in small, active animals with high metabolic rates. If you could travel back to the Jurassic and examine a small theropod up close, you would not see a scaly lizard. You would see something that looked more like a strange, toothy bird, its body covered in a coat of downy filaments that kept it warm through cool nights and helped regulate its temperature during the day. Over time, these simple filaments became more complex. Branching structures appeared, a central shaft with barbs radiating outward, creating flat, vein-like surfaces. These more complex feathers offered advantages beyond insulation. They could be used for display, patterns and colors that attracted mates or warned rivals. They could provide camouflage, breaking up the outline of a small animal against the dappled light of a forest floor. And eventually, on the arms of certain theropods, they became large enough and structured enough to catch air. Archaeopteryx is the most famous early bird, and its story is worth lingering on. Discovered in the limestone quarries of Germany in the 1860s, its fossils arrived at a moment of extraordinary scientific significance, just 2 years after Darwin published On the Origin of Species. Here, preserved in stone with exquisite detail, was exactly what Darwin's theory predicted. A creature that straddled the line between two groups, showing features of both reptiles and birds. It had feathers and wings, but also teeth, clawed fingers on its wings, and a long, bony tail. It was a mosaic, a snapshot of evolution in progress, caught in the act of becoming something new. Archaeopteryx was about the size of a raven. Its wings were capable of flapping, but it almost certainly could not fly the way modern birds do. It lacked the keeled sternum that provides the anchor points for powerful flight muscles in modern birds. Its skeleton was not as lightweight or as refined. It probably relied on short, clumsy flights or glides between trees, flapping in bursts to extend its range or escape danger. In the dense forests of the late Jurassic, where cover was plentiful and predators were everywhere, even short, awkward flights could mean the difference between survival and death. But Archaeopteryx was not alone. It was one of several small feathered theropods experimenting with the possibilities of the air during the late Jurassic and into the Cretaceous. The limestone deposits that preserved it did so because conditions there were exceptional: calm, oxygen-poor water at the bottom of lagoons that prevented decay and captured even the delicate impressions of feathers. Elsewhere, in places where preservation was less perfect, other feathered dinosaurs lived and died without leaving such detailed records.
Discoveries from China, made in the 1990s and beyond, have revealed a whole world of feathered theropods. Some of them not true birds at all, but close relatives that show just how widespread feathers had become. The significance of these early birds lies not in what they were during the Jurassic, but in what they would become. They were small, marginal animals, insignificant compared to the sauropods and allosaurs that dominated their world. A Jurassic Archaeopteryx
Hopping between branches was easy to overlook, easy to dismiss. But the lineage it belonged to would prove to be among the most resilient in the history of life. When the asteroid struck 66 million years ago and swept away every non-avian dinosaur on the planet, the birds survived. Today, there are over 10,000 species of birds, more species of birds than of mammals. They fill every continent, every habitat, from the deepest oceans to the highest mountains. The descendants of those clumsy, feathered theropods inherited the skies and have held them ever since. There is a deep irony here that is worth sitting with. The dinosaurs are not extinct. We say they are because the word has become shorthand for a vanished world. But every bird you hear singing in the morning is a dinosaur. The pigeons on your windowsill, the robins on your lawn, the crows in your parking lot. All dinosaurs, carrying forward a lineage that stretches back unbroken to the Jurassic, through the Cretaceous, through the asteroid impact, through the ice ages, all the way to this moment. The connection between you and the dinosaurs is not abstract or metaphorical. It is real, alive, and singing outside your window right now. But in the Jurassic, all of that was still in the future. The first birds were testing uncertain wings, flapping from branch to branch in forests where the real power still belonged to creatures far larger than themselves.
And those larger creatures, the sauropods and the theropods, and the stegosaurs and the plesiosaurs, still had many millions of years ahead of them. The Jurassic was drawing toward its close, but the age of dinosaurs was not ending. It was merely transitioning, shifting into its next phase, the Cretaceous, where new forms would arise and the drama of life on Earth would enter its most spectacular act. The Jurassic did not end with a bang. It faded into the Cretaceous gradually. A transition so slow and so blurred, the geologists still debate exactly where to draw the line between them. Some species that flourished in the late Jurassic persisted into the early Cretaceous without change. Others disappeared or declined, replaced by new forms better suited to conditions that were slowly, imperceptibly shifting. Stegosaurs faded, their ecological role eventually taken by ankylosaurs, heavily armored dinosaurs with club-like tails that would become the tanks of the Cretaceous.
Some sauropod lineages went extinct while others continued, and new groups that had been minor players in the Jurassic, like the titanosaurs, began to diversify. The fossils that tell us about the Jurassic world are themselves part of the story, because everything we have walked through tonight, every forest, every ocean, every herd of sauropods, every hunting allosaur, is known to us only because of traces left in stone, and the process by which those traces were preserved is as remarkable as the creatures they record. Most living things never become fossils. They decay, are consumed by scavengers, or are broken down by weather and erosion. For fossilization to occur, conditions must be precisely right. Rapid burial in sediment, protection from oxygen and decay, and millions of years of mineral replacement that slowly turns bone and shell into stone.
The rarity of this process means that every fossil is a small miracle, a moment frozen by chance that has survived the grinding passage of deep time. The most recognizable fossils are the bones, and they tell us far more than just the shape of an animal. By studying the internal structure of fossilized bone, paleontologists can determine how fast an animal grew, whether it was warm-blooded or cold-blooded, and even how old it was when it died. Growth rings, similar to tree rings, record annual cycles of fast and slow growth. In sauropod bones, these rings show rapid early growth, animals packing on tons of weight in their first 2 decades of life, before slowing as they approached adult size. Trackways add another dimension. When a herd of sauropods crossed a muddy floodplain, their weight pressed deep impressions into the soft ground. When that mud dried and hardened, it captured not just their footprints, but the story of their movement.
Parallel tracks show herds walking together.
Differences in stride length reveal adults and juveniles side by side. Occasionally, the tracks of a predator intersect with those of a herd, telling a story of pursuit or investigation. These frozen paths are more dynamic than bones alone can provide. They show behavior, social structure, and the interactions between species in real time. Fossilized nests and eggs open windows into reproduction. Some dinosaur nesting sites show that parents return to the same locations year after year, building nests in sandy banks or forest clearings and tending their eggs until they hatched. Eggshell fragments reveal details of structure and composition. Entire clutches have been found with embryos still inside, preserved at the moment before hatching. Tiny, curled skeletons that show what the youngest dinosaurs looked like. Plant fossils are equally valuable.
Impressions of fern fronds, conifer needles, and cycad leaves pressed into ancient mud show us the vegetation that sustained the herbivores. Some are so detailed that individual leaf veins are visible. Coal deposits formed from accumulated Jurassic plant matter tell us how productive the forests were, how much biomass they generated, and how that biomass was distributed across the landscape. Even coprolites, fossilized droppings, provide essential information. They contain fragments of the food an animal consumed, connecting predators to prey and herbivores to specific plants. Some coprolites are large enough to suggest they came from sauropods, giving us direct evidence of the enormous volume of food these animals process daily. The very act of studying these fossils connects us to the Jurassic in a way that reading about it cannot. When a paleontologist holds a sauropod vertebra, they are holding an object that was last touched by living tissue 150 million years ago. When they trace the outline of a fern frond in stone, they are looking at a leaf that photosynthesized under a Jurassic sun, converting light and carbon dioxide into the energy that eventually powered a dinosaur's muscles. The fossils are not just data. They are physical connections to a world that no human eye has ever seen, translated across deep time by the patient chemistry of mineral and stone. And every year, new fossils emerge from the rock, adding details to the picture, revising old assumptions, opening new questions. The story of the Jurassic is not finished. It is still being written, one bone at a time, one careful extraction at a time, one scientist kneeling in the dust and brushing away the sediment that has hidden a piece of the past for longer than the human mind can comprehend. The world was changing.
Continents were drifting farther apart, opening wider oceans, isolating populations, and creating the conditions for regional differences in dinosaur fauna. The climate was evolving too, with more pronounced temperature gradients between equator and poles, creating distinct climate zones that had been less sharply defined in the hothouse Jurassic. And somewhere, in a place and time we cannot yet pinpoint, a small, inconspicuous plant produced the first flower. That flower would change everything. The Cretaceous period lasted from about 145 million years ago to 66 million years ago, nearly 80 million years, longer than the Jurassic and far longer than the Triassic. It was during the Cretaceous that the dinosaur dynasty reached its fullest expression, producing the most famous and most diverse cast of characters in the entire Mesozoic. But the Cretaceous world was not a simple continuation of the Jurassic.
It was a transformation,
Driven by two forces that reshaped every ecosystem on the planet: the continued breakup of Pangaea and the rise of flowering plants. By the middle of the Cretaceous, the supercontinent was well and truly shattered. South America was pulling away from Africa, opening the South Atlantic. India was drifting north, beginning its long journey toward the collision with Asia that would eventually raise the Himalayas. Australia was separating from Antarctica. North America and Europe was splitting apart, with the Atlantic widening steadily between them. The world map was beginning to look recognizable, though the details were still wrong. India was an island, Australia was far south, and sea levels were so high that shallow seas flooded vast stretches of the interiors of continents, splitting North America in two with a waterway called the Western Interior Seaway. This fragmentation had profound consequences for life. Populations that had once been connected across Pangaea were now isolated on separate land masses. Isolation drives evolution. When a group of animals is cut off from its relatives, it evolves independently, adapting to local conditions. Over millions of years, those adaptations accumulate until the isolated population becomes a distinct species, then a distinct group of species, then something entirely new. The Cretaceous world was a world of regional faunas, each continent developing its own distinctive collection of dinosaurs, and the diversity this produced was staggering. But the most important transformation of the Cretaceous was botanical. Flowering plants, angiosperms, appeared in the fossil record around 130 million years ago and began to spread. At first, they were minor components of ecosystems still dominated by conifers and cycads. But they had advantages that the older plant groups could not match. They grew faster. They reproduced faster. They formed partnerships with insects, exchanging nectar for pollination services in relationships of mutual benefit that accelerated the evolution of both partners. They produced fruits that attracted animals, which ate the fruit and dispersed the seeds in their droppings. These strategies gave flowering plants an edge that the gymnosperms could not overcome, and by the late Cretaceous, angiosperms had conquered most terrestrial environments. The flowering plant revolution transformed every level of the food web. Insects diversified explosively, co-evolving with flowers in a dance of mutual adaptation that produced butterflies, bees, ants, and countless other forms. New plant communities supported new herbivores, which supported new predators. The forests of the late Cretaceous looked fundamentally different from those of the Jurassic. They had flowers, they had fruits, they had broad-leaved trees alongside the ancient conifers, and they hummed with insects that had no Jurassic equivalents. The dinosaurs of the Cretaceous reflected these changes. In North America, the late Cretaceous produced some of the most iconic dinosaurs in the popular imagination. Tyrannosaurus rex, the tyrant lizard king, patrolled what is now Montana, Wyoming, and the Dakotas, a predator unlike anything the Jurassic had seen. At 40 feet long and weighing perhaps 8 or 9 tons, Tyrannosaurus was not merely large, it was built for power. Its skull was massive, over 5 feet long, with jaws capable of generating bite forces that could crush bone. Unlike the slashing, flesh-tearing strategy of Allosaurus, Tyrannosaurus bit through bone, consuming its prey more completely. Its teeth were thick, conical, designed for penetration and destruction rather than slicing. Its arms, famously small, were probably not useless. Recent research suggests they may have been used for gripping during mating or for holding prey close. But they were clearly secondary to the jaws. Tyrannosaurus hunted with its mouth. Triceratops shared the late Cretaceous of North America with Tyrannosaurus, and the interaction between these two animals has become one of the most iconic predator-prey relationships in the fossil record. Triceratops was a ceratopsian, a group of herbivorous dinosaurs characterized by facial horns and bony frills. It weighed about 9 tons, with 3 horns on its face and a massive frill of bone extending backward from its skull. Those horns were weapons, capable of goring a predator, and the frill may have served both as a display structure and as protection for the neck.
Fossil evidence includes Triceratops horns with bite marks matching Tyrannosaurus teeth, and Tyrannosaurus bones with wounds that could have been inflicted by Triceratops horns. These animals knew each other. They fought each other. And the outcomes were not always in the predator's favor. Hadrosaurs, the duck-billed dinosaurs, were among the most successful herbivores of the late Cretaceous. They had batteries of hundreds of teeth packed into their jaws, constantly replaced as they wore down, allowing them to grind tough vegetation with remarkable efficiency. Some hadrosaurs had elaborate crests on their skulls, hollow, bony structures that were connected to their nasal passages and almost certainly functioned as resonating chambers, amplifying their calls.
Imagine a herd of hadrosaurs moving through a late Cretaceous forest, their calls echoing through the trees. Deep, resonant, haunting sounds that carried for miles, coordinating the herd, warning of predators, announcing their presence to the world. Ankylosaurs carried armor to its extreme, their bodies covered in bony plates, their tails ending in massive clubs of solid bone that could shatter the leg of an attacking predator. Pachycephalosaurs had domed skulls of dense bone, possibly used in headbutting contests for mates. Raptors, the dromaeosaurs, were fast, intelligent predators, many of them covered in feathers, hunting in groups with coordination that suggests a level of social behavior unusual for reptiles. The Cretaceous world was rich beyond imagining, populated by forms so varied and so strange that new ones are still being discovered every year. In the oceans, the Cretaceous was equally dramatic. Mosasaurs, marine lizards, relatives of modern monitor lizards, appeared and rapidly became the dominant ocean predators. Some grew to enormous sizes, 50 feet or more, with powerful jaws and streamlined bodies built for chasing prey through open water. Plesiosaurs continued to thrive, and some reached their largest sizes during the Cretaceous. Giant marine turtles cruised warm seas. Sharks diversified into forms both familiar and strange. Ammonites flourished in staggering variety, their shells coiling into shapes so diverse that they serve as one of the most important tools for dating Cretaceous rocks. In the skies, pterosaurs reached their pinnacle. Quetzalcoatlus, the largest flying animal ever to exist, had a wingspan of 33 to 36 feet, wider than a small airplane. It could have looked a giraffe in the eye while standing on the ground.
These enormous pterosaurs probably hunted on land as well as from the air, stalking across open plains like nightmarish storks, snatching up small dinosaurs and mammals with their elongated beaks. But the pterosaurs were beginning to share the skies with birds, which were diversifying rapidly during the Cretaceous, developing the keeled sternums and refined wing structures that would make them the supreme flyers of the modern world. The Cretaceous oceans had their own revolution alongside the botanical one on land. The Western Interior Seaway, a shallow body of warm water that split North America in two from the Gulf of Mexico to the Arctic, teemed with life. Schools of fish churned through its waters in numbers that darkened the shallows. Ammonites drifted in every size and shape, from coils smaller than a coin to spirals wider than a truck tire, their chambers filled with gas to control their buoyancy.
their tentacles reaching out to snare plankton and small prey.
Giant sea turtles, some with shells spanning over 6 feet, cruised the warm currents, feeding on jellyfish and vegetation. The seafloor was carpeted with oysters and clams, their shells piling into beds that would one day become the limestone cliffs of Kansas and the chalk deposits of the English coast. Above the seaway, the great pterosaurs soared on thermals rising from the warm water, scanning the surface for the flash of a fish breaking through. Along the shorelines, shorebird-like dinosaurs picked through tidal flats, leaving footprints that would fossilize in the mud. The boundary between land and sea was alive with traffic, animals moving back and forth, energy flowing between the terrestrial and marine worlds through rivers that carried nutrients to the coast and through predators that hunted in both realms. On the southern continents, the Cretaceous told a different story.
South America, still connected to Africa at the beginning of the period, but increasingly isolated as the South Atlantic widened, developed its own distinctive fauna. Titanosaurs, a group of sauropods that had been minor players in the Jurassic, exploded in diversity, becoming the dominant large herbivores across South America, Africa, India, and even Antarctica. Some titanosaurs reached sizes that rivaled or exceeded anything the Jurassic had produced. Argentinosaurus, from what is now Patagonia, may have weighed 70 tons or more, making it one of the heaviest land animals that has ever existed. These southern giants lived alongside their own predators, abelisaurs, a group of theropods with short, blunt skulls and powerful jaws that filled the apex predator role in the southern hemisphere the way tyrannosaurs did in the north. The separation of the continents meant that evolution was running parallel experiments on different land masses. In North America, tyrannosaurs and ceratopsians and hadrosaurs built one kind of ecosystem. In South America, titanosaurs and abelisaurs and a completely different cast of supporting characters built another. In Asia, yet another mix of species produced its own distinct community. Each continent was a separate laboratory, testing different combinations of predator and prey, different body plans, different survival strategies. The result was a global diversity of dinosaur life that exceeded anything the Jurassic had seen, even though the Jurassic is often remembered as the peak of the dinosaur age. And through all of this, the mammals waited. They had been present since the Triassic, more than 100 million years earlier, and for that entire span, they had remained small and marginal. Most Cretaceous mammals were no bigger than a cat. Many were nocturnal, hiding during the day and emerging at night when the dinosaurs were less active. They had developed warm-bloodedness, fur, specialized teeth, and the beginnings of the complex brains that would later define the mammalian lineage. But in a world dominated by dinosaurs, they could not break through into larger body sizes or more prominent ecological roles. The ceiling above them was too low, held in place by the dinosaurs' total dominance of the available niches. The mammals were patient. They had been patient since the Great Dying, since the early Triassic, since the long rebuilding. 165 million years of patience, of smallness, of scurrying in the shadows. And their patience was about to be rewarded. Because the Cretaceous, for all its richness and all its glory, was heading toward a moment that would change everything. The third catastrophe was approaching. And unlike the first two, which were fires from below, volcanoes splitting continents and poisoning atmospheres, this one would come from above. The late Cretaceous was an ecosystem in full bloom, the most complex and diverse terrestrial community the Earth had ever produced. To appreciate what the asteroid destroyed, you need to understand what was thriving in the millions of years before it struck. The forests of the late Cretaceous were genuinely different from anything that came before. Flowering plants had transformed the landscape. For the first time in Earth's history, trees with broad leaves stood alongside conifers. Magnolias bloomed in the understory. Early relatives of sycamores and laurels spread their canopies. Ferns and cycads remained, but they shared space with a botanical newcomer that was rapidly taking over. The colors of the Cretaceous forest were richer than the endless green of the Jurassic. Flashes of white and yellow and pink appeared in the understory, where flowers caught the light and attracted the insects that pollinated them. The coevolution between flowers and insects was one of the great creative explosions in the history of life. Plants that could attract pollinators with nectar and bright colors reproduced more successfully than those that relied on wind alone. Insects that could exploit those nectar sources had an advantage over those that could not. The result was an accelerating spiral of adaptation that produced bees, butterflies, moths, and ants in rapid succession, each group evolving new behaviors and body structures to exploit the new resources that flowers provided. The buzzing of a Cretaceous forest was louder and more varied than anything in the Jurassic, filled with the hum of pollinators that had not existed a few tens of millions of years earlier. These changes rippled through the food web. New insects meant new food for small vertebrates. New plants meant new food for herbivores.
The hadrosaurs, with their battery of grinding teeth, were particularly well adapted to processing the tough leaves and stems of flowering plants. Their success in the late Cretaceous, they were among the most abundant large herbivores across North America, Asia, and Europe, was likely linked to their ability to exploit the botanical revolution that angiosperms represented. The diversity of late Cretaceous dinosaurs was staggering. In what is now Western North America, the landscape supported a cast of characters that reads like an inventory of the most famous dinosaurs ever discovered. Tyrannosaurus rex at the top of the predator hierarchy. Triceratops in herds, their horns and frills catching the light. Herds of hadrosaurs like Edmontosaurus, their calls resonating across valleys. Ankylosaurs like Ankylosaurus, armored head to tail, their club tails capable of shattering the ankle of an attacking tyrannosaur. Pachycephalosaurs with their domed skulls, possibly used in contests for mates. Smaller theropods darting through the understory, many of them feathered, hunting lizards and mammals and eggs. And each of these animals had its own biology, its own behavior, its own story. Tyrannosaurus, for example, grew from a slender, long-legged juvenile into a massive, bone-crushing adult over a period of about 20 years. Bone studies suggest that Tyrannosaurus went through a growth spurt in its teenage years, gaining nearly over 2,000 pounds per year during a period of rapid transformation. A young Tyrannosaurus was a different animal from an adult, lighter, faster, probably hunting different prey. The ecological niche of the juvenile was different from the niche of the adult, which means that a single species was effectively filling two predator roles in the ecosystem. Triceratops underwent its own transformation as it grew. Juveniles had small horns and small frills.
As they matured, the horns lengthened, the frill expanded, and the overall shape of the skull changed dramatically. These changes were almost certainly related to social behavior, display, combat, species recognition. A herd of Triceratops would have included animals at every stage of growth, from small, hornless juveniles to massive adults with 3-foot-long brow horns and frills the size of dinner tables. The marine world of the late Cretaceous matched the land in diversity and drama. Mosasaurs had replaced the ichthyosaurs that had faded earlier in the Cretaceous, and they dominated the oceans with an authority that few marine predators have ever matched. Some mosasaurs reached lengths of 50 feet or more, their powerful jaws capable of crunching through the shells of giant sea turtles or the armor of ammonites. They were fast, agile, and numerous, the apex predators of a marine ecosystem that was itself richer and more complex than anything the Jurassic seas had supported.
Plesiosaurs continued to thrive alongside the mosasaurs, filling different ecological roles. Some had grown enormous. Elasmosaurus, for example, had a neck containing over 70 vertebrae, so long that it stretched like a serpent through the water, allowing the animal to probe into schools of fish from a distance without moving its massive body. Other plesiosaurs had shortened their necks and expanded their skulls, becoming powerful bite-force predators that competed with mosasaurs for larger prey. In the skies, the late Cretaceous saw both pterosaurs and birds reaching new levels of diversity. Quetzalcoatlus, the largest flying animal in Earth's history, soared over the plains of what is now Texas, its wings spanning 33 to 36 feet. On the ground, it would have stood as tall as a giraffe, stalking across open landscapes and snatching up small animals with its elongated beak. Smaller pterosaurs filled other niches. Fishing species along coastlines, insect eaters over forests. Species adapted to a wide range of environments. But they were sharing the sky increasingly with birds, which were diversifying rapidly and would ultimately outlast them. All of this, every horn, every frill, every grinding tooth, every coiled ammonite shell, every soaring pterosaur, was alive and thriving and evolving and competing in the final millions of years before the asteroid arrived. The late Cretaceous was not a declining world. It was not an ecosystem in decay, waiting for a merciful end. It was life at full volume, complex and diverse and powerful. And it was all swept away in a single day. The Deccan Traps, a massive volcanic province in what is now India, had already been erupting for hundreds of thousands of years before the asteroid hit, stressing ecosystems with gas emissions and climate fluctuations. Some scientists have argued that the Deccan volcanism weakened the biosphere enough that the asteroid impact was simply the final blow to a world already under strain. Others argue that the asteroid alone was sufficient to cause the extinction. The debate continues, and it may never be fully resolved. What is clear is that the combination of stresses, volcanic and extraterrestrial, created conditions that no ecosystem on Earth could withstand. A rock was falling through space. It had been falling for a very long time. And when it arrived, nothing on Earth would ever be the same again. 66 million years ago, on what might have been an ordinary day in the late Cretaceous, a day when Tyrannosaurus hunted and Triceratops grazed, and hadrosaurs called to each other across forests, and ammonites drifted through warm seas, an asteroid roughly 6 to 9 miles in diameter entered the Earth's atmosphere at a speed of about 12 miles per second. It was moving so fast that the air in front of it could not get out of the way, and it compressed into a superheated shockwave that ignited everything beneath it. The asteroid struck the shallow sea near what is now the Yucatan Peninsula of Mexico, creating the Chicxulub impact crater, a scar roughly 110 miles across that is still detectable in the geology of the region today. The impact released energy equivalent to billions of nuclear weapons detonating simultaneously. The ocean in the impact zone was vaporized instantly. The bedrock beneath it, limestone and gypsum, rich in sulfur and carbon, was pulverized
and launched into the atmosphere in a column of superheated rock and gas that punched through the stratosphere and into space. Earthquakes of magnitude 10 or greater rippled outward from the impact site, shaking the entire planet.
Tsunamis hundreds of feet high radiated across the Gulf of Mexico, crashing into the coastlines of what is now the southern United States and sweeping far inland. But the immediate devastation at the impact site was only the beginning. The material launched into the atmosphere, trillions of tons of pulverized rock, sulfur compounds, and soot from global wildfires, spread around the entire planet within hours. This blanket of debris blocked sunlight, plunging the Earth into darkness and cold. Temperatures dropped by more than 35 degrees Fahrenheit in some regions. Photosynthesis ceased as plants could no longer receive the sunlight they needed. Without plants, the herbivores starved. Without herbivores, the predators starved. The food web, which had taken millions of years to build, collapsed in months.
The sulfur compounds released from the vaporized rock fell back to Earth as acid rain, burning vegetation, acidifying fresh water sources, and dissolving the shells of marine organisms. The oceans, already stressed by the impact, suffered mass die-offs at every level. Ammonites, which had survived the Great Dying and the Triassic-Jurassic extinction and had thrived for hundreds of millions of years, were wiped out completely. Coral reefs, which had rebuilt after each previous extinction, collapsed again. Marine reptiles, the mosasaurs, the plesiosaurs, the giant marine turtles, vanished. On land, the non-avian dinosaurs, every sauropod, every theropod, every ceratopsian, every hadrosaur, every ankylosaur, died. Their reign, which had lasted 165 million years, ended in a geological instant. The pterosaurs, which had been the first vertebrates to master powered flight, died with them. So many species disappeared so quickly that the boundary between the Cretaceous and the Paleogene, the geological period that followed, is marked in the rock record by a thin layer of clay enriched in iridium, an element rare on Earth but common in asteroids. That layer is found in sediments around the entire world. It is a line drawn in stone, marking the moment when the Mesozoic ended and something new began. The parallel with the Great Dying is impossible to ignore, and it brings us back to the central thread of everything we have talked about tonight. The dinosaurs were born from catastrophe, the double catastrophe of the Permian extinction and the Triassic-Jurassic extinction, which cleared the ecological stage and allowed them to rise. And they died from catastrophe, a rock from space that did in a single day what the Siberian traps and the camp eruptions had done over hundreds of thousands of years.
66 million years ago, as the dust settled and the darkness lifted and the acid rain subsided, the world was quiet again. The forests were burned or dying. The oceans were acidic and empty. The great animals that had dominated every continent were gone. The silence was vast, pressing, and total. And in that silence, something was moving. Small, furry, nocturnal creatures were emerging from their burrows. They had been there all along. 165 million years of hiding in the shadows, of being small, of being marginal, of waiting. The mammals had survived the asteroid just as the dinosaurs had survived the camp eruptions. Not because they were superior, but because they happened to have traits that worked in that specific crisis. Small bodies need less food. Burrowing provides shelter from temperature extremes. Diverse diets mean flexibility when food sources disappear.
The same logic that had saved the dinosaurs from the Triassic extinction now saved the mammals from the Cretaceous one. And the inheritance passed again. Within 10 million years of the asteroid impact, mammals had diversified into forms that filled the ecological roles the dinosaurs had left vacant. Herbivores grew large, predators followed them. Some mammals returned to the sea, evolving into whales and dolphins, forms strikingly similar to the ichthyosaurs and plesiosaurs that had preceded them. A beautiful example of convergent evolution, where nature finds the same solutions to the same problems, regardless of which lineage is doing the solving. Some mammals took to the trees and eventually produced primates, and from primates came a species that would one day stand in museum halls, looking up at the bones of the creatures whose world it had inherited. You.
The recovery after the asteroid was, in some ways, the most remarkable of all three recoveries we have walked through tonight. Because unlike the Great Dying or the Triassic-Jurassic extinction, which unfolded over tens of thousands of years, the asteroid impact was instantaneous. One day the Cretaceous world existed, the next day it did not. The abruptness of the destruction made the recovery feel almost defiant, as if life itself was refusing to accept the verdict. In the first few thousand years after the impact, the world was a place of ash and silence. The fires had burned themselves out. The dust was settling from the atmosphere. The acid rain was fading as the sulfur compounds washed out of the sky. And in the devastated landscapes, the same pattern that had followed every previous catastrophe began again. Ferns were first. Their spores, tough and ubiquitous, germinated in the ash-covered soil, and within years, green was returning to a world that had been brown and grey.
The fern spike, as paleontologists call it, is visible in the sediment record at the Cretaceous-Paleogene boundary, a sudden surge of fern spores that marks the moment when plants began to reclaim the scorched earth. Behind the ferns came the flowering plants. And here the Cretaceous-Paleogene recovery differed from previous ones, because flowering plants had not existed during the earlier extinctions. Their faster growth rates, their seeds enclosed in protective fruits, their partnerships with insects, all of these gave them advantages in the race to recolonize the empty world. The forests that grew back after the asteroid were angiosperm forests, dominated by broad-leaved trees rather than the conifers that had led recovery in the Triassic. The botanical revolution that had begun in the Cretaceous continued through the extinction, and the post-impact world was built on a new kind of vegetation. The mammals, small and hidden during the entire age of dinosaurs, exploded into the empty spaces. Within 10 million years, a blink in geological time, they had diversified into forms that filled the ecological roles the dinosaurs had vacated. Herbivores grew large. Early horses, no bigger than dogs, browsed on the new vegetation. Predators followed, the ancestors of modern cats and dogs and bears, evolving teeth and claws to match the new prey available. Some mammals returned to the sea, beginning the long evolutionary journey that would produce whales, the largest animals ever to live on Earth, surpassing even the great sauropods in mass, though operating in the buoyancy of water rather than against the pull of land-based gravity. Some mammals took to the trees, developing grasping hands and forward-facing eyes that gave them depth perception. These primates, as they would come to be called, diversified in the tropical forests of the Paleogene, developing larger brains, more complex social behaviors, and eventually, much later, the capacity for language, for art, for science, for the kind of sustained curiosity that would one day lead a particular species of primate to dig bones out of rock and wonder what walked the earth before them. That species is you. You are standing at the current end of a chain that stretches back, unbroken, through every catastrophe and every recovery we have discussed tonight. The Great Dying did not break the chain. The camp eruptions did not break it. The asteroid did not break it. The chain runs through Lystrosaurus, through the early archosaurs, through the dinosaurs, through the small mammals that hid in burrows while the world burned above them, through the primates, through the hominids, through every ancestor that lived and reproduced and passed its genes forward, one generation at a time, for hundreds of millions of years. So here, at the end of this long journey, let me draw the thread together. Because the story we have walked through tonight is not just a collection of facts about ancient animals. It is a story about a pattern that has repeated 3 times in the history we have covered, and that is still operating right now, at this very moment, in the world outside your window. The pattern is simple. Catastrophe creates emptiness. Emptiness creates opportunity. Opportunity creates dynasties. And dynasties last until the next catastrophe.
The Great Dying, 252 million years ago, wiped the slate nearly clean and allowed the archosaurs to rise. The Triassic-Jurassic extinction, 201 million years ago, removed the pseudosuchians that had dominated the Triassic and handed the world to the dinosaurs. The asteroid impact, 66 million years ago, ended the dinosaurs' reign and opened the way for mammals. Each time, the survivors were not the strongest or the smartest. They were the ones whose traits happened to match the specific demands of that specific catastrophe. Lystrosaurus survived the Great Dying because it could dig burrows and eat anything. The dinosaurs survived the camp eruptions, possibly because of their efficient lungs and fast growth. The mammals survived the asteroid because they were small, flexible, and hidden underground. And each time, the survivors looked around at an empty world and began to fill it, not through any plan or intention, but simply because life expands wherever there is space. Give it empty niches, and it will fill them. Give it time, and it will build complexity. Give it millions of years, and it will produce giants, produce flyers, produce swimmers, produce thinkers. The pattern is relentless, and it is ongoing. The world you live in right now is the product of the most recent iteration of this pattern. The mammals that inherited the Earth after the asteroid impact have had 66 million years to diversify, and they have filled the planet with whales, and bats, and elephants, and mice, and primates, and wolves, and dolphins, and eventually a species that developed the ability to wonder about all of this. You are part of the pattern. Your existence is a direct consequence of a rock from space hitting the Yucatan Peninsula 66 million years ago.
If that asteroid had missed,
If it had arrived 6 hours earlier, or 6 hours later, passing harmlessly through the space the Earth had just occupied, or had not yet reached, the dinosaurs might still be here. Mammals might still be small, nocturnal, marginal, and you would not exist. Think about that for a moment. Your life and the lives of everyone you have ever known are downstream of an event that happened 66 million years ago, caused by a rock that had been traveling through space for millions of years before it intersected the path of a planet at exactly the wrong moment. The dinosaurs did not fail. They were not inferior. They ran the world for 165 million years, far longer than mammals have had so far, and they produced forms of life so extraordinary that we are still trying to understand them. Their end was not a judgment on their fitness. It was a catastrophe, random, violent, and total, that no amount of adaptation could have prevented.
And the birds remind us that the dinosaurs did not entirely vanish. Every morning, when you hear birds singing, you are hearing the voice of the Mesozoic, the lineage that produced Archaeopteryx in the Jurassic, that diversified through the Cretaceous, that somehow survived the asteroid while every other dinosaur died. That lineage is still here. Over 10,000 species of birds, on every continent, in every habitat. The dinosaurs are not gone. They transformed. They shed their size and their teeth and their bony armor, and they became something light and swift and musical. The sparrows at your feeder are the living heirs of a dynasty that stretches back 230 million years, unbroken. The continents, too, carry the story forward. The Atlantic Ocean is still widening, still pushing the Americas away from Europe and Africa, still doing what it began doing in the Jurassic.
The Himalayas are still rising as India continues its collision with Asia, a collision that began in the Cretaceous. The Earth has not stopped moving. The forces that split Pangaea and shaped the Mesozoic world are still at work, still reshaping the planet, about half an inch per year, and the pattern has not stopped operating. The world you live in is the product of the last catastrophe, the asteroid impact, but it is not immune to the next one. Whether that next catastrophe comes from space, from the Earth's interior, or from the activities of one particular species of primate, the pattern will continue. Emptiness will be created. Survivors will fill it. A new dynasty will arise, and it will last until the next reset. But that is a story for another time, or no time at all, because the pattern operates on scales so vast that no individual life, human or otherwise, can witness it. The Great Dying unfolded over tens of thousands of years.
The camp eruptions lasted hundreds of thousands. The asteroid impact was instantaneous, but the recovery took millions. These are timescales that exceed any human experience, any human planning, any human imagination. They are the timescales of the Earth itself, patient beyond comprehension, operating by rules that do not care about any single species, no matter how dominant it might feel. And perhaps that is the most comforting thought to carry into sleep tonight. The Earth has been through worse than anything you have seen. It has been through the Great Dying, which killed 95% of marine species. It has been through the camp eruptions, which killed 76% of everything. It has been through an asteroid impact that ended a 165 million year dynasty. And every single time, life came back. Not the same life, not immediately, but life. Persistent, adaptable, endlessly creative life, filling every niche, testing every strategy, building complexity from the ashes of catastrophe. You are part of that life. You carry within you the legacy of every catastrophe and every recovery that came before. The atoms in your body have cycled through the biosphere since long before the dinosaurs appeared. Some of those atoms may have been part of a fern in a Triassic forest, or a conifer in a Jurassic canopy, or a sauropod crossing a floodplain, or a small mammal hiding in a burrow as the asteroid struck. Matter does not disappear, it transforms. And the transformation connects you to every age that has ever been and to every age that will come after. So let the story settle. Let the weight of those millions of years rest lightly on you, the way you might rest your hand on the warm bark of a tree and feel the life humming beneath it. The dinosaurs are not gone. They are in the birds, they are in the rocks,
They are in the shape of the continents. They are in the pattern of catastrophe and renewal that has governed the earth since life began. And you, lying here, breathing slowly, feeling the day ease away, you are part of that pattern too. Your body knows it, even if your mind forgets. The heartbeat in your chest follows the same rhythm that has pulsed through living things for billions of years. The breath that fills your lungs uses the same oxygen that Jurassic forests produced. The sleep that is coming for you is the same rest that every creature in every age has needed to continue.
So let it come. Let the giants rest. Let the oceans settle. Let the continents drift a fraction of an inch while you are still. The story will be here in the morning if you want it. The fossils will still be waiting in the rock. The birds will still be singing outside your window.
And the Earth will keep turning, the way it has for 4.5 billion years, patient and persistent and endlessly alive. Close your eyes. The ash has settled. The world is green again. And somewhere, in the quiet of this night, life is still going. It has always been going. And it will keep going, long after this moment has passed into the deep time that holds everything. Rest now. You have earned it. Good night.